Before we descend into the darkness, I want to ask a favour. If you enjoy this story, please use your hype points on this video. It helps the channel more than you possibly know. If you're listening on Spotify, leaving a review makes a massive difference. And if you'd like, comment what time it is and where in the world you're listening from. We absolutely love seeing where everyone is tuning in. And of course, if you enjoy the content, consider subscribing. Now let's begin. You're walking across a room. It's something you've done thousands of times, a movement so automatic that you rarely give it a thought. You decide to go somewhere. Your legs begin to move, and within moments you arrive at your destination. The distance between where you started and where you ended seems like a single, unbroken span of space that you simply cross. There's no mystery to it, no puzzle to solve. Motion feels obvious, natural, as certain as breathing. But what if that certainty is hiding something? What if the simple act of crossing a room contains within it a challenge so profound that it has troubled philosophers and mathematicians for more than 2,000 years? This is exactly what the ancient Greek philosopher Zeno of Elea proposed when he presented what has come to be known as Zeno's dichotomy paradox. Zeno wasn't trying to convince anyone that motion is impossible. After all, he could see people walking around just as easily as anyone else. Instead, he was doing something more subtle and more unsettling. He was reframing the way we think about movement, transforming what seems like a single continuous journey into a sequence of required steps that, by the logic of his argument, never ends. The paradox begins with a simple scenario, one that feels completely ordinary. Imagine you want to travel from one point, which we'll call point A, to another point, which we'll call point B. Maybe point A is your bed, and point B is your bedroom door. Maybe it's the start of a hallway, and the other end. The specific distance doesn't matter. What matters is that there's a beginning, an end, and space in between. To reach point B from point A, you must travel the entire distance. That much is obvious. But here's where Zeno introduces his challenge. Before you can reach point B, you must first reach the halfway point between A and B. Let's call that halfway point C. This requirement sounds perfectly reasonable. After all, if you're travelling from A to B, you will indeed pass through the midpoint. There's nothing controversial about acknowledging that the halfway point exists, or that you'll reach it on your way to the destination. But now, Zeno takes the next step. Before you can reach point C, the halfway point between A and B, you must first reach the halfway point between A and C. Let's call that point D. Again, this seems fair enough. If C is located halfway between A and B, then there must be a point halfway between A and C, and you'll have to pass through it to get to C. And now the pattern becomes clear, and with it, the paradox begins to take shape. Before you can reach point D, you must reach the halfway point between A and D. Before you can reach that point, you must reach the halfway point between A and that point. Each time you identify a next point you need to reach, you can apply the same logic. There must be a point halfway between where you are and where you're trying to go, and you must reach that intermediate point. First, this process can be repeated forever. No matter how many times you divide the distance, there is always another halfway point waiting, another intermediate goal that must be accomplished before the previous one can be reached. Each individual requirement in this chain sounds perfectly sensible on its own. Each halfway point is a real location, a genuine position in space. There's nothing imaginary or magical about these points. They exist as surely as the starting point and the destination exist. The paradox emerges not from any single step in the reasoning, but from what happens when you follow the reasoning all the way through. If you must reach the halfway point before reaching the destination, and you must reach the halfway point to the halfway point before that, and the halfway point to that point before that, and so on without end, then it seems you're being asked to complete an infinite number of tasks before you can finish your journey. This is where the mind begins to stumble. An infinite number of tasks sounds like an infinite amount of work. Even if each individual task is simpler than the one before it, even if each step is smaller and takes less time, the list itself never ends. There is no final halfway point you can reach that will free you from the need to reach another one. The sequence continues forever, always demanding one more intermediate goal before allowing you to move forward. And if that's the case, if arriving at point B genuinely requires completing an infinite number of steps, then how can you ever finish? More troubling still, how can you even begin? To begin the journey, you must reach the first halfway point. But to reach the first halfway point, you must reach the halfway point to that point. And to reach that point, you must reach the halfway point to it. The logic seems to push you backward, always finding another starting requirement before you can satisfy the previous one. It's as if you're trying to start a task, but discovering that every starting point has its own prerequisite, and that prerequisite has its own prerequisite, in an endless regress that never allows you to take the first step. The journey from A to B, which seems so straightforward at the outset, now appears impossible. Not because the distance is too great, not because you lack the ability to move, but because the very structure of the journey seems to demand something that can't be done. The completion of a process that has no end. This is the heart of Zeno's dichotomy paradox. It doesn't claim that motion is obviously impossible. It doesn't rely on magic or fantasy. It simply takes an ordinary journey, applies what seems like straightforward logical reasoning, and arrives at a conclusion that conflicts dramatically with everyday experience. We know that people walk across rooms. We know that motion happens. We can see it, experience it, rely on it. And yet the paradox seems to prove, through careful argument, that motion cannot happen. The tension between logical conclusion and observable reality is what gives the paradox its power and its staying power. It's been debated, analysed, and discussed for millennia because it touches on something fundamental about how we understand space, time, and the nature of infinity. The trap hidden within Zeno's argument becomes clearer when we examine the language and assumptions built into the paradox. The key word that carries much of the logical weight is must. You must reach the halfway point before reaching the destination. You must reach the halfway point to the halfway point before reaching the halfway point. These statements use must in a way that seems to establish a sequence of requirements, a checklist of accomplishments that have to be completed in order. The structure feels rigid and absolute, as if the universe itself is enforcing these rules, demanding that each intermediate point be consciously reached, acknowledged, and completed before the next. One can begin. This is where intuition starts to mislead us. The paradox treats the infinite list of halfway points as if it were a to-do list that must be worked through one item at a time, with each item requiring a discrete act of completion before the next item can be addressed. Think about how you approach a normal list of tasks. If you have 10 things to do, you do one, then another, until all 10 are finished. The list has a beginning, a middle, and an end. You can track your progress. You can know when you're done. But what happens if the list never ends? What if every time you complete a task, the list generates another one before it? In that case, you could work forever and never finish, because finishing requires reaching the end of the list, and the list has no end. This is the mental model that makes Zeno's paradox feel so compelling. It suggests that crossing from point A to point B requires completing a checklist that goes on forever. And since you can't complete a never-ending checklist, you can't complete the journey. The logic feels airtight. The infinite sequence of halfway points isn't just a quirk of mathematical description. It seems to impose an actual burden on the traveller, a burden that consumes infinite time precisely because it involves infinitely many steps. Time must be spent on each step, and if there are infinitely many steps, then infinite time must be consumed, which means the journey never finishes. But this is where we need to slow down and question the assumption. Does passing through infinitely many halfway points actually require infinitely many discrete acts of completion? Does the traveller need to consciously check off each intermediate point before moving to the next? Or is something else happening? Zeno's argument forces us to confront an idea that doesn't fit neatly into everyday intuition: the relationship between infinity and totality. Just because something can be divided into infinitely many parts doesn't automatically mean that putting those parts together results in something infinite. In fact, it's entirely possible for infinitely many parts to add up to a finite whole. To understand this, we need to think carefully about what happens when you add up the distances covered by each segment of the journey. The first segment, from point A to the first halfway point, covers half the total distance. The second segment, from that halfway point to the next, covers half of the remaining distance, which is 1/4 of the total. The third segment covers half of what's left after that, which is 1/8 of the total. The pattern continues. Each segment covers half of the remaining distance, which means each segment is half the length of the previous segment. So the distances are getting smaller rapidly: 1/2, then 1/4, then 1/8, then 1/16, and so on. Now, if we add up these fractions, we're asking, what is 1/2 plus 1/4 plus 1/8 plus 1/16, continuing forever? Our everyday intuition about addition might suggest that adding infinitely many things must give you an infinite total. After all, if you keep adding, doesn't the sum keep growing? But there's a crucial detail here. The things you're adding are getting smaller very quickly, and they're getting smaller in such a way that the total sum doesn't grow without bound. Instead, it approaches a specific value. It gets closer and closer to that value with each term you add, never quite reaching it if you stop after finitely many terms. But in the infinite sum, the total is exactly that value. In this case, the sum of 1/2 plus 1/4 plus 1/8 and so on, forever, equals exactly 1. The infinite sequence of fractions adds up to a finite total, the whole distance from A to B. This is the mathematical idea of a convergent series. When we say a series converges, we mean that as you add more and more terms, the running total gets closer and closer to some finite number, and in the limit, the idealized case where you've added infinitely many terms, the total is exactly that finite number. The infinite sum doesn't blow up to infinity. It settles down to a specific finite value. This is a profound realization because it breaks the mental link between infinitely many parts and infinite total. Infinitely many parts can form a finite whole as long as the parts are shrinking quickly enough. The same logic applies to time. If we assume that you travel at a constant speed, then the time it takes to cover each segment is proportional to the distance of that segment. The first segment takes half the total time. The second takes 1/4 of the total time. The third takes 1/8, and so on. When you add up all these time intervals, you get the same kind of convergent series: 1/2 plus 1/4 plus 1/8, continuing forever, which equals 1. The total time to complete all infinitely many steps is finite. It's the same amount of time it would take to walk directly from A to B at a constant speed. The infinity in the number of steps doesn't translate to infinity in the total time required. This is where the paradox begins to dissolve. The conclusion that you can never reach point B was based on the assumption that completing infinitely many steps requires infinite time. But once we recognize that the steps are getting shorter in such a way that their total duration is finite, that assumption collapses. You do pass through infinitely many halfway points, in a sense, but you don't spend infinite time doing so. The journey is completed in a finite span of time, and the destination is reached, just as everyday experience tells us it is. The paradox was never really about whether motion is possible. It was about whether our intuitive understanding of infinity aligns with the mathematical reality of how infinite processes can behave. This resolution has elegance to it, but it also opens up deeper questions about what we mean by infinity and how it relates to the physical world. Zeno's dichotomy forces us to confront the fact that our minds are not naturally equipped to handle infinity in the context of everyday experience. In daily life, we almost never encounter truly infinite collections of things. We count finite numbers of objects, complete finite lists of tasks, experience finite stretches of time. When we try to extend our intuitions about the finite to the infinite, we often go astray. Infinity doesn't behave like a very large finite number. It has its own rules, its own logic, and those rules can be counterintuitive. One of the key insights that emerges from thinking about Zeno's paradox is the difference between discrete processes and continuous ones. A discrete process is made up of separate, distinct steps. Each step is its own individual event, and you move from one to the next in a clearly defined sequence. A to-do list is a discrete process. You do task 1, then task 2, then task 3. Each task is separate, and you can count how many you've completed at any given time. But continuous processes are different. In a continuous process, there are no gaps, no distinct steps that can be counted off one by one. Motion through space, at least in the classical understanding, is continuous. You don't jump from one position to the next with nothing in between. You flow smoothly through all the intermediate positions. The paradox arises in part from trying to treat a continuous process, motion through space, as if it were a discrete process, a checklist of positions to reach. When we list all the halfway points and say, you must reach this one, then this one, then this one, we're imposing a discrete structure onto something that's actually continuous. We're carving up the smooth flow of motion into an infinite number of artificial stopping points, and then acting as if each stopping point is a separate task that must be completed. But in reality, the traveller doesn't stop at each halfway point. They don't pause, check it off a list, and then proceed to the next one. They simply move continuously, passing through all those points without treating them as discrete events. This distinction between discrete and continuous is fundamental to understanding why the paradox feels so strange, even after the mathematical resolution is presented. The mathematics shows us that an infinite sum can have a finite total, which explains how the journey can be completed in finite time. But it doesn't fully address the conceptual unease that comes from thinking about infinitely many steps. That unease comes from our tendency to think in discrete terms, to imagine each step as a separate event, and to feel that infinitely many events must somehow be too many to complete. The shift in perspective required to dissolve the paradox is to recognize that motion isn't actually made up of discrete events in the first place. It's a continuous flow, and the halfway points are just mathematical markers we can use to describe the motion, not actual stopping points that must be individually conquered. The idea of a limit is central to making sense of this. In mathematics, a limit describes what happens as you carry out a process further and further, even if you never actually complete the process in a finite number of steps. When we say the infinite sum of 1/2 plus 1/4 plus 1/8 approaches 1, we're talking about a limit. As you add more and more terms, the sum gets closer and closer to 1, and the limit of the sum, as the number of terms goes to infinity, is exactly 1. Limits allow us to talk rigorously about infinite processes without requiring that those processes be completed in the way we complete finite tasks. The total distance covered by passing through all the halfway points is the limit of the sum of the segment distances, and that limit is the full distance from A to B. This concept of a limit is what allows modern mathematics to handle infinity in a precise way. Before the development of calculus and formal analysis, questions about infinite sums and infinite divisions were deeply puzzling. There was no clear framework for deciding what an infinite sum should equal, or whether it should equal anything at all. Zeno's paradoxes were genuine philosophical problems without clear mathematical solutions. But with the tools of modern mathematics, particularly the rigorous definition of limits developed in the 19th century, these questions can be answered definitively. An infinite series either converges to a finite value or it doesn't, and we have precise methods for determining which is the case. In the case of the series that describes the journey from A to B, the answer is clear. It converges to the total distance, and the journey is completed in finite time. Yet even with this mathematical resolution, there's a sense in which the paradox retains its philosophical interest. It pushes us to ask deeper questions about the nature of space and time, questions that go beyond mathematics and into the foundations of physics and metaphysics. One of the most profound questions raised by Zeno's paradox is whether space and time are truly continuous. We've been assuming that you can move smoothly through space, passing through infinitely many intermediate positions. But is that actually how the world works? Or is space at some fundamental level made up of discrete units, smallest possible distances that can't be subdivided further? In classical physics, space and time are treated as continuous. You can divide a distance in half, and then divide that half in half, and keep going as far as you like, at least in principle. There's no smallest unit of length, no indivisible atom of space. The same goes for time. You can divide a second into milliseconds, then microseconds, then nanoseconds, and keep going. The continuum model works beautifully for describing the motion of everyday objects, and even for many phenomena in modern physics. But when we push to the smallest scales, to the realm of quantum mechanics and theories of quantum gravity, questions about the structure of space and time become more subtle. Some theories in modern physics suggest that space and time might not be continuous at the smallest scales. There are ideas about a quantum of space, or a Planck length, which is an incredibly tiny distance, about 10 to the minus 35 meters, below which the usual notions of space and distance might break down. If space is fundamentally discrete at this scale, then in principle, you couldn't keep dividing distances forever. Eventually you'd reach a smallest possible unit, and you couldn't go smaller. Similarly, there might be a smallest unit of time, a Planck time, which is about 10 to the minus 44 seconds. If time is discrete at this scale, then motion wouldn't be a perfectly smooth flow, but rather a series of incredibly tiny jumps from one moment to the next, though these jumps would be so small that they'd be impossible to detect with any current technology. If space and time are discrete, does that resolve Zeno's paradox in a different way? In a sense, yes. If there's a smallest possible distance, then you can't keep dividing the journey in half forever. Eventually, you'd reach a segment that's only one quantum of space long, and you couldn't divide it further. The number of steps in the journey would be very large, but finite, not infinite. And if the number of steps is finite, there's no puzzle about completing them all. You just take one step, then another, until you're done. The paradox would be sidestepped because the premise that you can divide the distance infinitely would turn out to be false. But this resolution, if it even applies, doesn't diminish the importance of the paradox. For one thing, we don't know for certain whether space and time are discrete at the Planck scale, or whether that scale just represents the limits of our current theories. For another, even if space and time are discrete, the paradox still serves as a valuable thought experiment about how we reason about infinity and continuity. It reveals assumptions we make about the nature of motion and the structure of reality, and it challenges us to think carefully about concepts we usually take for granted. The paradox has driven centuries of philosophical and mathematical inquiry, leading to insights about limits, convergence, and the nature of the continuum. Insights that are valuable regardless of whether the physical universe turns out to be continuous or discrete at the deepest level. There's also a deeper philosophical question lurking beneath the paradox, a question about what motion actually is. When you walk across a room, what is happening? One way to think about it is that motion is a series of positions occupied at different times. At one moment, you're at position A. A short time later, you're at a position slightly closer to B. A bit later still, you're even closer. If we imagine plotting your position at every instant of time, we get a continuous path from A to B, a smooth curve that shows how your position changes as time passes. In this view, motion is fundamentally about occupying different positions at different times, and the motion itself is just the collection of all these position-time pairs. But is that all there is to it? Or is motion something more than just a series of static positions? This is a question that philosophers have debated for centuries. One perspective, sometimes called the at theory of motion, says that motion is nothing more than being at different places at different times. To be in motion is simply to be at one position at one time and at another position at another time. There's no additional ingredient, no mysterious flow or passage that needs to be added to explain what motion is. You're just at different places at different times, and that's all there is to it. This view is compatible with thinking of a journey as a series of infinitely many positions, each occupied at a specific instant, and it fits well with the mathematical resolution of Zeno's paradox. The journey is completed because you occupy all the necessary positions at all the necessary times, and the total time required is finite because the infinite series of time intervals converges. But some philosophers find this view unsatisfying. It seems to reduce motion to a static picture, a frozen collection of snapshots. Where is the actual moving in this account? When you walk across a room, it feels like you're doing something, not just existing at a series of positions. There's a sense of flow, of continuous change, that seems to be missing from a purely positional account. This leads to an alternative view, sometimes called the process view of motion, which holds that motion is a genuine activity, a process that unfolds over time rather than just a collection of static states. In this view, being in motion is fundamentally different from being at rest, even at a single instant. A moving object has a kind of dynamic quality that a stationary object lacks. Zeno's paradox touches on this debate because it highlights the tension between thinking of motion as a smooth, continuous process and thinking of it as a series of discrete positions. If motion is continuous, then dividing it into infinitely many steps is an artificial imposition, a way of describing the motion that doesn't capture its essential, flowing nature. But if motion is just a matter of being at different places at different times, then the infinite division is perfectly natural. It's just a detailed description of all the positions occupied during the journey. The paradox doesn't definitively settle this philosophical question, but it forces us to confront it and to think carefully about what assumptions we're making when we talk about motion. Another layer of complexity comes from thinking about time itself. We usually imagine time as a kind of container in which events happen, a flowing river that carries us from past to future. But what if time isn't like that? What if time, like space, is just a dimension, a coordinate that helps us describe when things happen but doesn't flow in any literal sense? In this view, often associated with the block universe picture in physics, all moments of time exist equally. The past, present, and future are all equally real, just located at different positions along the time dimension. Your journey from A to B exists as a four-dimensional path through space-time, with one dimension for space and one for time. The entire journey from start to finish is laid out in the block universe, and there's no sense in which the present moment moves along that path. The path just exists, all at once, as a fixed part of the space-time structure. In this picture, Zeno's paradox takes on a different flavour. The question isn't really about whether you can complete the journey in time, because all moments of the journey already exist in the block universe. The journey is already complete, in a sense, because the entire space-time path is part of the fixed structure of reality. The paradox becomes more about whether we can make sense of the idea that this path is made up of infinitely many points, and whether having infinitely many points poses any conceptual problem. The mathematical resolution still applies. The path has a finite total length in space and a finite total duration in time, even though it's composed of infinitely many space-time points. But the philosophical question shifts from how can you complete the journey to how can we make sense of a continuum that contains infinitely many points. This is a deep question in the philosophy of mathematics and the philosophy of physics. The mathematical continuum, the set of real numbers, is an abstract structure that captures the idea of smooth, continuous variation. It's incredibly useful for describing physical phenomena, from the motion of planets to the flow of fluids to the oscillation of electromagnetic fields. But it's also a very strange structure when you think about it carefully. It's infinitely dense. Between any two distinct points on the continuum, there are infinitely many other points. It's uncountably infinite. There are more real numbers than there are integers, even though there are infinitely many integers. And it's perfectly divisible. You can always find a midpoint between any 2 points, no matter how close together they are. The fact that the mathematical continuum has these properties doesn't necessarily mean that physical space and time have them too. It's possible that the continuum is just a mathematical idealization, a convenient tool for calculations that doesn't perfectly represent the underlying structure of reality. But whether or not space and time are truly continuous, the mathematical continuum has proven to be an extraordinarily powerful framework for understanding the natural world. And Zeno's paradox, by challenging our intuitions about continuity and infinity, has helped sharpen our thinking about what the continuum means and how it should be used. One of the reasons the paradox remains compelling, even after the mathematical resolution is understood, is that it speaks to a mismatch between different ways of thinking. On one hand, we have our everyday, intuitive understanding of motion, which tells us that crossing a room is simple and straightforward. We don't consciously think about halfway points or infinite divisions. We just walk and we arrive. On the other hand, we have a logical, analytical approach that breaks down the journey into components and asks how those components fit together. When we apply this analytical approach to motion, we discover the infinite sequence of halfway points, and suddenly, what seemed simple becomes puzzling. This is a common pattern in philosophy and science. Our intuitions are shaped by everyday experience, which involves finite numbers of things, finite stretches of time, and processes that have clear beginnings and endings. When we try to extend our thinking to the infinite, to the infinitesimally small, or to the very structure of space and time, our intuitions often lead us astray. We need different tools, mathematical tools, conceptual tools, to navigate these domains. And part of the value of Zeno's paradox is that it teaches us this lesson in a vivid and memorable way. It shows us that even the most ordinary, familiar phenomena can hide deep conceptual puzzles when we examine them closely enough. The resolution of the paradox through the concept of convergent series is satisfying in a mathematical sense, but it doesn't entirely eliminate the psychological strangeness. Even when you understand that the sum of 1/2 plus 1/4 plus 1/8 equals 1, there's still something counterintuitive about the idea that you can add infinitely many things and get a finite result. Our minds are wired to think that more things means bigger total. And while that's true for finite sums, it's not necessarily true for infinite ones. The specific way in which the terms in the series decrease matters enormously. If the terms decrease fast enough, the sum converges. If they don't, the sum grows without bound. To appreciate this, consider a different series. 1 plus 1/2 plus 1/3 plus 1/4, and so on. This is called the harmonic series, and it behaves very differently from the series in Zeno's paradox. Even though the terms are getting smaller, 1/3 is smaller than 1/2, 1/4 is smaller than 1/3, they don't get small fast enough to make the sum converge. If you keep adding more and more terms of the harmonic series, the total keeps growing, slowly but relentlessly, without ever settling, down to a finite limit. The harmonic series diverges to infinity, so just because you're adding terms that are getting smaller doesn't guarantee a finite sum. The rate at which they shrink is crucial. In Zeno's series, the terms shrink by a factor of 1/2 each time. Each term is exactly half the previous term. This geometric decrease is fast enough to ensure convergence. In the harmonic series, the terms shrink much more slowly. The nth term is 1/n, which decreases, but only as 1 divided by the term's position in the sequence. This slower decrease isn't enough to prevent the sum from growing indefinitely. Understanding this distinction requires some mathematical sophistication, and it's part of why the study of infinite series was such a significant development in the history of mathematics. It gave mathematicians the tools to distinguish between different kinds of infinite processes, and to say precisely which ones result in finite totals and which don't. The development of calculus in the 17th century by Newton and Leibniz was driven in part by questions related to infinite sums and infinitesimal quantities. Calculus provides a framework for dealing with change and motion, and at its heart are concepts like limits, derivatives, and integrals, all of which involve infinite processes in one way or another. When you calculate the derivative of a function, you're essentially finding the slope of a curve by considering what happens as you zoom in closer and closer, taking the limit as the interval you're examining shrinks to 0. When you calculate an integral, you're finding the area under a curve by dividing it into infinitely many, infinitesimally thin rectangles and adding them up. These techniques allow mathematicians and scientists to solve problems involving motion, change, and accumulation, and they rest on a rigorous understanding of limits and convergence. In the centuries after Newton and Leibniz, mathematicians worked to place calculus on a firmer logical foundation. The early pioneers of calculus had powerful intuitions and techniques, but they sometimes struggled to explain exactly what they meant by an infinitesimal, or what it meant to sum infinitely many quantities. These conceptual issues were gradually resolved, most fully in the 19th century, through the work of mathematicians like Cauchy, Weierstrass, and others, who developed the epsilon-delta definition of a limit and made the notion of convergence precise. With these tools, it became possible to prove rigorously that certain infinite sums converge to specific values, and to build all of calculus on a solid logical foundation. Zeno's paradox, in this light, was a precursor to these developments, an early example of a puzzle that could only be fully resolved with the mathematical machinery that took millennia to develop. But even with all this mathematical sophistication, the paradox retains a kind of haunting quality. There's something about the idea of infinite division that continues to feel strange, even when you understand the mathematics. Perhaps this is because infinity itself is inherently beyond our direct experience. We can imagine very large numbers, we can work with them mathematically, but we can't truly grasp infinity in the way we grasp finite quantities. Infinity is a limit concept, an idealization, something we approach but never reach in any concrete physical sense. And so, when we're asked to think about infinitely many steps, infinitely many divisions, infinitely many halfway points, we're being asked to think about something that transcends everyday experience. It's no wonder that our intuitions sometimes rebel. There's also a sense in which the paradox highlights the gap between description and reality. The infinite sequence of halfway points is a way of describing the journey from A to B, but it's not the only way, and it's not necessarily the most natural way. You could just as easily describe the journey as a continuous path, a smooth motion from start to finish, without breaking it into discrete segments at all. The choice to focus on the halfway points is a choice about how to describe the motion, not a necessary feature of the motion itself. The paradox arises when we take this particular description and treat it as if it imposes actual constraints on what can happen. But in reality, the traveller doesn't need to complete the infinite sequence of halfway points in any active sense. They just move, and the halfway points are locations they pass through along the way, not tasks they need to accomplish. This raises an interesting question about the relationship between mathematical descriptions and physical reality. Mathematics gives us incredibly powerful tools for describing the world, for making predictions, for understanding patterns and structures. But mathematical descriptions are abstractions. They pick out certain features of reality and represent them using numbers, equations, geometric shapes, and other formal structures. The question is, how closely does the mathematical description match the underlying reality? Is the universe itself fundamentally mathematical, so that the mathematical description is capturing the true nature of things? Or is mathematics just a useful language for describing patterns we observe without necessarily revealing the deeper essence of what's going on? Zeno's paradox doesn't answer this question, but it raises it in a sharp way. If space and time are truly continuous, then in some sense they really do contain infinitely many points. And the mathematical description, using real numbers and infinite series, is capturing something true about their structure. But if space and time are discrete, or if they have some more exotic structure that doesn't correspond neatly to the mathematical continuum, then the infinite divisibility in the mathematical description is an artifact of the model, not a feature of reality. We might still use the continuous model because it's convenient and accurate for most purposes, but we'd recognize that it's an approximation, not a perfect representation. Current physics doesn't give us a definitive answer to whether space and time are continuous or discrete at the most fundamental level. General relativity, Einstein's theory of gravity, treats space-time as a smooth continuum. The equations of general relativity are differential equations which rely on the assumption that space-time is infinitely divisible. On the other hand, quantum mechanics, the theory that describes the behavior of particles and fields at small scales, introduces a kind of discreteness through quantization. Certain quantities like energy and angular momentum can only take on specific discrete values in quantum systems, not a continuous range. But even in quantum mechanics, space and time themselves are usually treated as continuous, at least in the standard formulation of the theory. The quest to unify general relativity and quantum mechanics into a single theory of quantum gravity is one of the major challenges in theoretical physics, and the question of whether space and time are continuous or discrete is intimately tied up with this quest. Some approaches to quantum gravity, like loop quantum gravity, suggest that space has a discrete structure at the Planck scale, with a kind of granularity built into the fabric of spacetime itself. Other approaches, like string theory, work within a continuous spacetime framework, but introduce additional dimensions and exotic structures. The ultimate nature of space and time remains an open question, one that physicists continue to investigate through both theoretical work and, where possible, experimental tests. In the meantime, Zeno's paradox serves as a reminder of how deeply counterintuitive the infinite can be, and how carefully we need to think when we reason about it. The paradox has been a catalyst for mathematical and philosophical progress over the centuries, prompting thinkers to develop more precise definitions, more rigorous arguments, and more sophisticated frameworks for dealing with infinity and continuity. It has helped shape our understanding of limits, convergence, and the nature of the continuum, and it continues to be a valuable teaching tool, a vivid illustration of how seemingly simple questions can lead to profound insights. One of the beautiful things about the paradox is that it doesn't require any specialized knowledge to grasp its basic form. Anyone can understand the setup. You want to go from A to B, but first you have to reach the halfway point. And before that, you have to reach the halfway point to the halfway point, and so on. The puzzle is immediately clear, even to someone with no background in mathematics or philosophy. But fully resolving the paradox, understanding why motion is possible despite the infinite division, requires engaging with some fairly deep ideas about infinity, limits, and convergence. In this way, the paradox serves as a bridge between everyday intuition and advanced mathematics, a problem that's simple to state but rich in implications. There's also something almost playful about the way Zeno's argument works. It takes an action that everyone knows is possible, walking across a room, and shows that, if you think about it in a certain way, it seems impossible. It's a kind of intellectual magic trick, where the conclusion is obviously false, but the reasoning appears airtight. The challenge is to figure out where the trick is, to identify the hidden assumption or the subtle error in reasoning that makes the impossible conclusion seem to follow. And the resolution, when it comes, isn't just about pointing out a mistake, it's about understanding something new, something that wasn't obvious before, that infinite sums can have finite totals, that continuous motion isn't the same as a discrete sequence of tasks, that our intuitions about infinity need to be refined and corrected. This process of confronting a paradox, wrestling with it, and ultimately resolving it through deeper understanding is central to intellectual progress. Paradoxes are valuable precisely because they challenge us, because they reveal gaps or inconsistencies in our current thinking. They force us to question assumptions we didn't even realize we were making. And when we resolve a paradox, we don't just eliminate a puzzle, we gain new insight into the concepts involved. Zeno's paradoxes, including the dichotomy, have played this role in the history of thought. They've pushed mathematicians to develop calculus and rigorous analysis. They've prompted philosophers to think carefully about the nature of motion, time, and infinity. And they've helped scientists articulate more clearly what their theories say about the structure of space and time. It's worth noting that Zeno formulated several paradoxes, not just the dichotomy. Another famous one is the Achilles and the tortoise paradox, which has a similar structure but a different framing. In that paradox, the swift Achilles races against a slow tortoise, and the tortoise is given a head start. Zeno argues that Achilles can never overtake the tortoise because by the time Achilles reaches the tortoise's starting point, the tortoise has moved a little bit ahead. By the time Achilles reaches that new position, the tortoise has moved a bit further. Each time Achilles reaches where the tortoise was, the tortoise has advanced, and so Achilles can never quite catch up. The resolution is similar to the dichotomy. The infinite sequence of catching up steps corresponds to a convergent series, and Achilles does overtake the tortoise in finite time. But the different framing makes the paradox feel distinct, and it highlights different aspects of the same underlying issue. There's also the arrow paradox, which takes a different approach. Zeno argues that at any single instant of time, an arrow in flight is not moving. It's just located at a particular position with no motion happening at that instant. But if the arrow isn't moving at any instant, how can it be moving at all? This paradox probes the question of what motion is at an instant, and it connects to the philosophical debate about whether motion is a state an object can be in at a single moment, or whether it only makes sense to talk about motion over an interval of time. These paradoxes, taken together, form a coherent challenge to common sense notions of motion and change, and they've been debated and analysed for over 2 millennia. Returning to the dichotomy, the paradox's enduring appeal lies in its simplicity and its depth. On the surface, it's a straightforward logical argument about a simple scenario, but beneath the surface, it touches on fundamental questions about the nature of reality, the structure of mathematics, and the limits of human intuition. It asks us to think about what it means to complete an infinite process, what it means for space and time to be continuous or discrete, and what it means for a journey to have infinitely many intermediate stages. These aren't just abstract philosophical questions, they're questions that have implications for how we understand the physical universe and how we use mathematics to describe it. For someone lying in bed thinking about Zeno's paradox, there's a quiet comfort in the way it all comes together. The paradox presents a puzzle that seems insoluble, a logical trap with no escape. But then, with the introduction of the concept of convergence, the trap opens up. The infinite sequence of steps, which seem to make motion impossible, is revealed to be compatible with motion after all. The journey from A to B can be divided into infinitely many parts, and yet the journey is completed in finite time. The mathematical framework of limits and series provides a precise, rigorous way to understand how this is possible. And while the philosophical questions about the nature of motion and the structure of space-time remain open, the paradox no longer seems like an insurmountable obstacle. It becomes instead a window into the subtle and beautiful ways that mathematics, philosophy, and physics intertwine. There's something deeply satisfying about seeing how a problem that seemed so intractable can be dissolved through careful reasoning and the right conceptual tools. It's a reminder that human understanding is capable of making progress, that puzzles can be solved, and that the world, for all its complexity and strangeness, is not fundamentally incomprehensible. Zeno's Dichotomy, which starts with the simple act of walking across a room, ends up teaching us about infinity, continuity, limits, and the nature of space and time. It shows us that the familiar can be mysterious and that the mysterious can be understood. And in that journey, from puzzlement to understanding, there's a kind of intellectual peace, a satisfaction that comes from seeing how the pieces fit together. As you think about the paradox, about the infinite sequence of halfway points and the convergent series that makes the journey possible, you might find that your mind begins to relax. The initial tension of the paradox, the feeling that something must be wrong, gives way to a calm recognition that the resolution makes sense. The infinite doesn't have to be frightening or chaotic. It can be tamed, understood, incorporated into a coherent picture of how things work. The journey from A to B, which Zeno tried to make seem impossible, is just a journey after all. You take a step, and then another, and then another, and before long, you've arrived. The halfway points are there, infinitely many of them, but they don't stop you. They're just markers on the path, points you pass through on your way to the destination. And the destination is reached, just as it always was, just as you knew it would be from the start. In the end, Zeno's Dichotomy. Paradox is not proof that motion is impossible. It's proof that intuition can misread infinity, that our everyday understanding of how things work sometimes needs to be refined when we venture into the realm of the infinite and the infinitesimal. It's a lesson in humility, a reminder that the world is more subtle than it appears, and that careful thought can reveal depths beneath the surface of even the most ordinary experiences. The paradox has travelled through more than 2,000 years of intellectual history, prompting discussions, inspiring mathematical discoveries, and challenging assumptions. And it continues to do so because the questions it raises are timeless, and the insights it offers are profound. The simple act of walking across a room, of moving from one place to another, contains within it all the complexity of infinity and continuity, all the subtlety of limits and convergence. Zeno saw this, and he crafted a paradox that would force others to see it too. The paradox asks us to slow down, to think carefully, to question what we take for granted. And in doing so, it opens up a world of mathematical and philosophical richness, a world where the infinite is not just a vague idea, but a precise concept with clear rules and surprising consequences. The halfway points stretch out before you, infinitely many, each one half the distance of the one before, and together they sum to the whole. The journey is divided, yet complete. The steps are endless, yet the destination is reached. And in that paradox and its resolution, there is a kind of quiet wonder, a glimpse of the deep structure that underlies the everyday world, a reminder that reality is both stranger and more beautiful than we might have imagined. The next story is about to begin. Please relax and enjoy. The word full carries a simple meaning in everyday life. When every seat in a theatre is taken, we say the theatre is full. When every parking space in a lot is occupied, we say the lot is full. And when every room in a hotel has a guest sleeping in it, we say the hotel is full. The logic feels obvious and unshakable. If there's no empty space left, nothing more can fit. This understanding rests on something so fundamental, we rarely think about it. The fact that the things we're counting are finite. A theatre has a specific number of seats. A parking lot has a specific number of spaces. A hotel has a specific number of rooms. When we match guests to rooms, one person per room, and we run out of rooms, that's the end of the story. The hotel is full, and the next person who arrives must be turned away or sent somewhere else. This feels not just true, but necessarily true, like a law of nature, rather than a choice we've made about how to use words. But this certainty depends entirely on limits. It depends on there being a last room, a highest number, a final edge to the list. In the world we inhabit, every collection we encounter in daily life has this property. Even when we talk about very large numbers, thousands of hotel rooms, millions of people in a city, billions of stars in a galaxy, we're still talking about finite quantities. They're big, but they have boundaries. They can be counted, even if the counting would take longer than a human lifetime. And because they're finite, the rules of full remain intuitive. If you have 100 rooms and 100 guests, you're full. If you have 100 rooms and 101 guests, someone doesn't get a room. The math is simple, the outcome is clear, and our intuition stays intact. The concept of fullness in the finite world is tied closely to the idea of matching. When we say a hotel is full, what we really mean is that there's a perfect one-to-one correspondence between the set of rooms and the set of guests. Each room has exactly one guest, each guest has exactly one room, and there's nothing left over on either side. This kind of matching is how we understand equality of size in everyday contexts. Two sets are the same size if you can pair up their elements with no leftovers. If you have 5 chairs and 5 people, and everyone sits down with no one standing and no chair empty, you know the sets are equal. The matching proves it. This matching principle works beautifully for finite sets because finite sets have clear, definite sizes. You can count the elements, arrive at a specific number, and compare that number to other numbers. 10 is bigger than 5. 20 is bigger than 10. The relationships are straightforward, stable, and consistent with our physical experience of the world. When you add something to a finite set, it gets bigger. When you remove something, it gets smaller. When you split a finite set into parts, each part is smaller than the whole. These rules feel so natural that we might not even recognize them as rules. They seem like facts about reality itself. Hilbert's hotel is a thought experiment that keeps the word full, but removes the one thing that makes it behave the way we expect: finiteness. It was proposed by the German mathematician David Hilbert, not as a real architectural plan, but as a way to explore what happens to our logic when we step into the strange territory of the infinite. The paradox doesn't ask us to imagine something physically possible. Instead, it asks us to follow a chain of reasoning into a place where our everyday rules stop working, and stranger, more flexible rules take over. It's a paradox in the sense that it produces results that feel contradictory, even though every step in the argument is perfectly logical. And by walking through it slowly, we can begin to see how infinity reshapes ideas that seem rock solid in the finite world. The setup is simple to describe, but it contains a quiet revolution in its premise. Imagine a hotel with infinitely many rooms. The rooms are numbered 1, 2, 3, 4, and so on, continuing without end. There is no last room. If you walk down the hallway and pick any room number you like, say room 1,000,000, there are still infinitely many rooms beyond it. Room 1,000,001, room 1,000,002, room 1,000,003, stretching forward forever. The numbers don't stop. They don't approach some final door and then halt. They simply keep going, always producing the next number, always offering another room. Now imagine that every single one of these infinitely many rooms is occupied. Every room has a guest. Room 1 has a guest, room 2 has a guest, room 3 has a guest, and this pattern continues forever. There is no room, no matter how far down the hallway you walk, that stands empty. In this sense, the hotel is full. Every available space is being used. Every bed has someone in it. If we were dealing with a finite hotel, this would mean the end of the story. No more guests could be accommodated. The manager would hang a sign that says, "No vacancy," and turn people away at the door. But in Hilbert's hotel, something different becomes possible, and the key to understanding it lies in the structure of the numbering itself. The word infinite here doesn't just mean very large, it means the list of rooms never ends. There is no highest number. No matter which room you point to, there's always a next one. This endlessness isn't a vague metaphor, it's a precise mathematical property. The rooms are countably infinite, meaning they can be put into a one-to-one correspondence with the natural numbers 1, 2, 3, 4, and so on forever. This structure, this endless progression, with a clear rule for moving from one number to the next, is what allows the paradox to operate. The natural numbers themselves form the foundation of counting. They're the numbers we learn as children, the numbers we use to enumerate objects and measure quantities in discrete units. 1 apple, 2 apples, 3 apples, first place, second place, third place. The natural numbers start at 1 and proceed in order, each number exactly 1. More than the previous number, with no gaps, no breaks, no sudden jumps. This orderly progression feels deeply familiar, almost comforting in its predictability. And because the progression never ends, the natural numbers form an infinite set, the most basic, the most intuitive infinite set in mathematics. When we say Hilbert's hotel has infinitely many rooms, we mean it has exactly as many rooms as there are natural numbers. We can match each room to a number. Room 1 corresponds to the number 1, room 2 corresponds to the number 2, and so on. This matching is perfect and complete. Every room gets a number, every number gets a room, and the correspondence stretches on forever. This is what mathematicians mean by countably infinite, a set that can be counted, using the natural numbers, even though the counting never finishes. Imagine a new guest arrives at the hotel in the middle of the night. They walk up to the front desk, tired and hoping for a room. In a normal, finite hotel, the manager would check the registry, see that every room is occupied, and apologise. There's nothing to be done. But in Hilbert's hotel, the manager smiles and says there's no problem at all. They pick up the phone and make an announcement to every guest currently in the building. The message is simple. Please move from the room you're in now to the room with the next number. If you're in room 1, move to room 2. If you're in room 2, move to room 3. If you're in room 3, move to room 4. And so on. For every guest, forever. This shift feels impossible at first. If the hotel was full before, how can anyone move? Where is there space to move into? But follow the logic carefully. The guest in room 1 moves to room 2, but room 2 is occupied. So, where does that guest go? They move to room 3. But room 3 was also occupied. So where does that guest go? They move to room 4. And this continues, each guest stepping into the next room, which was occupied but is now being vacated by its previous occupant, who is also stepping forward. The crucial insight is that every room has a next room. There is no last room where the chain of moves would get stuck. The guest in room 1 million moves to room 1,000,001. The guest in room 1 billion moves to room 1,000,001,001. No matter how far out you go, the move can happen because the sequence never ends. Every current guest still has a room after the shift. Nobody's left without a place to stay, and because everyone has moved forward by one, room 1 is now empty. The new guest can move into room 1, and the hotel has accommodated them without adding any new rooms, without expanding the building, without doing anything except rearranging who is where. Think about this carefully, because it reveals something profound. In a finite hotel with, say, 100 rooms, all occupied, you cannot shift everyone to the next room, because there is no room 101. The person in room 100 has nowhere to go. The chain of moves breaks down at the boundary, at the limit of the hotel's capacity. But Hilbert's hotel has no such boundary. The capacity isn't a wall you hit. It's a horizon that keeps receding as you approach it. Every move that needs to happen can happen because the structure supports it infinitely. This is the first shock of the paradox. The hotel was full in the sense that every room was occupied, but it still had the capacity to accommodate someone new. The word full starts to feel slippery. In the finite world, being full means having no capacity left. But in Hilbert's hotel, being full and having infinite capacity can coexist. The paradox doesn't rely on tricks or wordplay. It relies on the simple fact that infinity behaves differently than any large finite number. You can take something infinite, shift it, and create space that wasn't there before, even though nothing was added. Now the paradox deepens. Imagine not just one new guest arriving, but infinitely many new guests. A bus pulls up to the hotel, and this bus has infinitely many seats, numbered 1, 2, 3, and so on, each with a passenger. They all step out and walk up to the front desk, hoping for rooms. In a finite hotel, this would be absurd. If the hotel had 1,000 rooms and they were all full, the arrival of even 11 new guests would be a problem. The arrival of infinitely many guests would be unthinkable. But in Hilbert's hotel, the manager remains calm. They make a different announcement this time, one that uses a more dramatic reshuffling strategy. The instruction is this: every current guest should move from the room they're in now to the room whose number is double their current room number. If you're in room 1, move to room 2. If you're in room 2, move to room 4. If you're in room 3, move to room 6. If you're in room 10, move to room 20. If you're in room 100, move to room 200. This pattern continues for every guest, no matter what room they started in. Everyone moves to a room with a number that's twice as large as their original room. Take a moment to follow what happens. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. The guest in room 4 moves to room 8. Notice that the guests are now spread out differently. They're no longer in consecutive rooms. They're only in the even-numbered rooms. 2, 4, 6, 8, 10, 12, and so on. Every current guest has moved into an even-numbered room, and because there are infinitely many even numbers, there's a unique even room for every guest. No two guests end up in the same place. Nobody is left without a room. But now look at what's left behind. If all the current guests are in the even-numbered rooms, what about the odd-numbered rooms? Room 1 is empty. Room 3 is empty. Room 5 is empty. Room 7 is empty. In fact, every odd-numbered room is now vacant. And there are infinitely many odd numbers. 1, 3, 5, 7, 9, and so on forever. The manager now has infinitely many empty rooms. One for each of the infinitely many new guests. Guest 1 from the bus can move into room 1. Guest 2 from the bus can move into room 3. Guest 3 from the bus can move into room 5. The pattern continues, matching each new guest to a unique odd-numbered room. The result is startling. The hotel was full before the bus arrived. Every room had a guest. But by rearranging the current guests using the doubling rule, the hotel created infinitely many vacancies. Not just one vacancy, as with the single new guest, but infinitely many. And all the new guests, infinite in number, fit perfectly into these newly opened spaces. The hotel didn't expand. No new rooms were built. The structure of the hotel is exactly the same as it was before, but the capacity has absorbed an entire infinite group of newcomers. This reveals something deep about the way infinity operates. The even numbers are a subset of the natural numbers. Not every natural number is even, only half of them are in a sense. But there are still infinitely many even numbers, and they can be matched one-to-one with all the natural numbers. You can pair 1 with 2, 2 with 4, 3 with 6, and so on, continuing forever without ever running out of pairs. This means the even numbers, despite being part of the natural numbers, are the same size in a precise mathematical sense. They have the same cardinality. This is impossible in the finite world. If you have 10 objects and you take a proper subset of them, say 5 objects, the subset is smaller. But with infinite sets, a proper subset can have the same size as the whole. This is one of the signature features of infinity, one of the ways it defies our everyday intuition. Consider what this means for our understanding of size and containment. In the finite realm, part of always means smaller than. If you have a basket of apples and you remove some apples to make a smaller pile, the smaller pile contains fewer apples than the original basket. This relationship is so fundamental to our experience that it shapes how we think about quantity itself. But in the infinite realm, this relationship breaks down. You can have a collection that's entirely contained within another collection, yet the two collections can be matched up perfectly, element by element, with nothing left over on either side. The even numbers sit entirely within the natural numbers. Every even number is a natural number, but not every natural number is even. So the even numbers are a proper subset. They're part of the whole, but not all of it. And yet, if you try to count the even numbers, you'll never finish, just as you'll never finish counting the natural numbers. Both sets are infinite in exactly the same way. Both can be listed in a sequence that goes on forever. Both have the same size when size is measured by the ability to create one-to-one correspondences. Now imagine the paradox taken even further. Instead of one bus with infinitely many passengers, imagine infinitely many buses arrive, each carrying infinitely many passengers. This sounds like chaos, like a situation that couldn't possibly be managed, but even this can be handled, and the method for doing so involves a kind of careful organisation that mathematicians call a pairing function or enumeration strategy. The idea is to find a way to assign every single arriving person, every passenger on every bus, a unique room number, so that nobody overlaps and nobody is left out. One way to think about this is to imagine laying out all the arriving passengers in a grid. The first bus has passengers numbered 1, 2, 3, and so on. The second bus also has passengers numbered 1, 2, 3, and so on. The third bus does the same. You can picture this as rows and columns. The first row is the passengers from the first bus. The second row is the passengers from the second bus, and so on. The grid stretches infinitely in both directions. Infinitely many rows, infinitely many columns. The challenge is to count through this grid in a systematic way that eventually reaches every single person. The trick is to move through the grid diagonally. Start at the top left corner with the first passenger from the first bus and assign them to room 1. Then move to the first passenger from the second bus and assign them to room 2. Then move to the second passenger from the first bus and assign them to room 3. Then move to the third passenger from the first bus, then the second passenger from the second bus, then the first passenger from the third bus. You're zigzagging through the grid, touching each diagonal in turn, making sure every position eventually gets counted. This method guarantees that every passenger, no matter which bus they came from, and no matter what their seat number was, eventually gets a unique room number. The process never ends, but it also never leaves anyone behind. To see why this works, imagine the grid as a two-dimensional array of positions. Each position is identified by two numbers, the bus number and the seat number. The person in seat 5 on bus 3 would be at position 3-5. The person in seat 1 on bus 1 would be at position 1-1. Now to convert these two-dimensional positions into one-dimensional room numbers, you need a systematic way to count through them. The diagonal method does exactly this. You count all positions where the sum of the two coordinates equals 2. That's just position 1-1. Then you count all positions where the sum equals 3. That's positions 1-2 and 2-1. Then you count all positions where the sum equals 4. That's positions 1-3, 2-2 and 3-1. And so on. Each diagonal contains finitely many positions, so you can count through each diagonal completely before moving to the next. And because every position has some finite sum of coordinates, every position appears on some diagonal. This means every passenger eventually gets assigned a room number. The method is systematic, exhaustive, and organised. There's no randomness, no guessing, no possibility of missing someone, or assigning two people to the same room. The point here isn't to memorise the exact method. The point is to see that even when you have infinity stacked on top of infinity, infinitely many groups, each with infinitely many members, it's still possible to organise everything into a single infinite list. The total number of arriving passengers is infinite, but it's a countable infinity, the same kind of infinity as the natural numbers. And because the hotel also has a countable infinity of rooms, the two can be matched up. The paradox isn't magic, it's organisation. It's the realisation that infinite lists can be rearranged, combined, and fitted together in ways that would be impossible if any of the quantities involved were finite. This capacity for reorganisation is one of the most striking features of countably infinite sets. You can take two countably infinite sets and merge them into one, and the result is still countably infinite. You can take infinitely many countably infinite sets and combine them, and the result remains countably infinite. The infinity doesn't grow in the sense of becoming a different kind of infinity. It stays the same type, the same cardinality, even though intuitively it feels like you're adding more and more. In the finite world, addition always increases size. If you have 10 things, and you add 10 more things, you have 20 things, which is larger than 10. If you combine 100 groups of 10 things each, you have 1,000 things. The size grows proportionally to what you add. But with countable infinity, adding another countable infinity doesn't make it bigger. It's still countably infinite. You can pour one infinite set into another, combine infinitely many infinite sets, and the result is still something that can be matched one-to-one with the natural numbers. This seems to violate basic arithmetic. How can infinity plus infinity equal infinity? How can infinity times infinity equal infinity? But these equations only seem wrong if we think of infinity as a number, in the usual sense. Infinity isn't a number that participates in ordinary arithmetic. It's a property of sets, a description of their size or cardinality. And the cardinality of countably infinite sets behaves according to its own rules, rules that don't match the arithmetic of finite numbers. What Hilbert's hotel really teaches us is that infinity is not a single simple quantity. In everyday language, we often use the word infinite as if it means unimaginably large or beyond counting. But in mathematics, infinity comes in different types, different sizes, each with its own structure and behaviour. The infinity of the natural numbers, 1, 2, 3 and so on, is called countably infinite. This doesn't mean you can actually count all the way to the end, because there is no end. It means the elements can be put into a sequence, a list with a first element, a second element, a third element, and so on, where every element eventually appears somewhere in the list. The rooms in Hilbert's hotel are countably infinite. They're numbered with the natural numbers, so they can be listed in order. Room 1, Room 2, Room 3, continuing forever. This structure is what allows all the reshuffling moves to work. When the manager asks guests to shift from room N to room N plus 1, or from room N to room 2 times I in, these instructions make sense because every room has a number, and every number has a clear relationship to the other numbers. The infinity is structured, ordered, and therefore manageable in a logical way. But not all infinities are countable. There are larger infinities, infinities that cannot be put into a one-to-one correspondence with the natural numbers, no matter how clever your pairing strategy. The most famous example is the set of real numbers, which includes not just the whole numbers, but also all the fractions, all the decimals, all the numbers that fill the continuous line between any 2 points. The real numbers are uncountably infinite. If you tried to list them all in a sequence, you would always leave some out. There's no way to match them up with the natural numbers the way you can with the even numbers or the passengers on infinitely many buses. The distinction between countable and uncountable infinity was discovered through a brilliant argument known as Cantor's diagonal argument. The argument shows that if you try to make a list of all real numbers between 0 and 1, you can always construct a new real number that isn't on your list. You do this by going down the list and making sure your new number differs from the first number in the first decimal place, differs from the second number in the second decimal place, differs from the third number in the third decimal place, and so on. This new number can't be anywhere on your list because it differs from every listed number in at least one decimal place. So any attempt to list all the real numbers must be incomplete. The real numbers are too numerous, too densely packed to be counted even with an infinite counting process. This discovery was revolutionary. It meant that infinity itself comes in a hierarchy of sizes. The smallest infinite size is countable infinity, the size of the natural numbers. But there are larger infinities, sizes that exceed countable infinity, and in fact there's no largest infinity at all. For any infinite size there's always a larger one. This hierarchy is fundamental to modern set theory, the branch of mathematics that studies collections and their properties. Hilbert's hotel operates in the realm of countable infinity, the smallest kind of infinite size. But even within this realm, the paradox reveals something fundamental and strange. A countably infinite set can be put into perfect correspondence with a proper subset of itself. The even numbers are a proper subset of the natural numbers, meaning they're contained within the natural numbers, but they're not the whole set. Yet there are just as many even numbers as there are natural numbers in total. You can pair them up one-to-one with no leftovers on either side. This is impossible in the finite world. If you have a finite set and you remove some elements, the subset is genuinely smaller. But with infinite sets, part of doesn't always mean smaller in the way we expect. This property, that an infinite set can be matched with a proper subset of itself, is sometimes used as a definition of infinity. A set is infinite if and only if it can be put into one-to-one correspondence with some proper subset of itself. This definition captures something essential about infinity. It's a kind of size that doesn't diminish when you remove part of it, a kind of container that doesn't empty when you pour part of it out. Consider the integers, which include all positive and negative whole numbers as well as 0. The integers extend infinitely in both directions. Negative infinity on one side, positive infinity on the other. How many integers are there compared to natural numbers? You might think there are twice as many, since the integers include both positive and negative numbers. But in fact the integers are also countably infinite, and they're the same size as the natural numbers. You can create a listing that counts them all. 0, 1, -1, 2, -2, 3, -3, and so on. This listing eventually reaches every integer, proving that the integers can be matched one-to-one with the natural numbers. So even though the integers seem more numerous, because they extend in both directions, they're the same infinite size as the natural numbers, Or consider the rational numbers, the fractions. Every fraction, every ratio of two integers is a rational number. There are infinitely many fractions between any two whole numbers. Between 0 and 1 alone, there are infinitely many fractions, 1/2, 1/3, 1/4 and so on, plus 2/3, 3/4, and countless others. It seems like the rational numbers must be a much larger set than the natural numbers. But remarkably, the rationals are also countably infinite. You can list them systematically using a method similar to the diagonal counting used for the buses. The rationals are dense. They're packed infinitely tightly along the number line, but they're still countable. They're still the same size as the natural numbers. This is one of the most counterintuitive results in all of mathematics. The rational numbers fill the number line densely, with infinitely many fractions between any 2 points. Yet they're the same size as the natural numbers, which are spread out with gaps between them. Density and size are different properties. A set can be densely packed and still be countable. The key is whether you can organize the set into a list, a sequence that eventually includes every element. These examples show that countable infinity is remarkably robust. You can spread elements out, pack them densely, extend them in multiple directions, combine them in complex ways, and as long as you can find a systematic way to list them all, they remain countably infinite. The size doesn't change. The cardinality stays the same. Countable infinity is the kind of infinity that yields to organization, that can be tamed by systematic enumeration. But the real numbers resist this organization. The continuum, the complete number line with all its points, is uncountably infinite. It's a larger infinity, a different kind of vastness. You cannot make a list of all real numbers. You cannot assign each one a natural number position in a sequence. There are simply too many of them. They're packed so densely, so continuously, that any attempt to count through them will miss most of them. If Hilbert's Hotel tried to accommodate all the real numbers, it would fail. There aren't enough rooms. Even with infinitely many rooms, numbered with the natural numbers, the hotel cannot house the uncountable. The real numbers exceed the capacity of any countably infinite structure. This is a kind of fullness that cannot be overcome by reshuffling. The hotel would be genuinely, irreversibly full, with infinitely many real numbers left outside, unable to find a room. This distinction between countable and uncountable infinities is profound, because it shows that infinity itself is not a single destination, but a landscape, with different regions, different sizes, different characteristics. The paradox of Hilbert's Hotel works precisely because the hotel's capacity matches the size of the sets arriving. All the guests, all the buses, all the passengers are countably infinite, matching the countably infinite rooms. The manager can always find a way to reorganize because the type of infinity on both sides is the same. This matching of infinities is reminiscent of how finite numbers work, but with crucial differences. If you have 10 rooms and 10 guests, you can match them perfectly. If you have 10 rooms and 20 guests, you cannot. The size matters. With infinite sets, the type of infinity matters in a similar way. Countably infinite guests can fit into a countably infinite hotel. Uncountably infinite guests cannot. The concept of size still applies, but it requires understanding the different levels of infinity. The paradox also touches on the nature of mathematical existence. The hotel doesn't exist physically, but it exists as a concept, as a logical structure that follows consistent rules. In mathematics, this kind of existence is often sufficient. Mathematicians study objects that cannot be built in the physical world. Perfect circles, infinite sets, higher dimensional spaces, because these objects have logical coherence and yield insights about structure, pattern, and relationship. Hilbert's Hotel is such an object. It cannot be built, but it can be understood. Its rules can be followed, its consequences can be explored, and those consequences reveal truths about infinity that apply far beyond the hotel itself. The reshuffling strategies used in the hotel are examples of bijections, one-to-one correspondences between sets. A bijection is a pairing where every element in the first set matches exactly one element in the second set, and vice versa, with nothing left unpaired on either side. Bijections are the fundamental tool for comparing sizes of sets. If two sets can be put into bijection, they have the same cardinality, the same size. The function that sends each natural number n to the even number 2 times n is a bijection between the natural numbers and the even numbers. The diagonal counting method is a bijection between the two-dimensional grid of bus and seat positions and the one-dimensional list of natural numbers. These bijections are not arbitrary. They're carefully constructed to ensure that every element gets paired exactly once. In the finite world, constructing a bijection is straightforward. You just match elements one by one until you run out. In the infinite world, you need a rule, a formula, a systematic procedure that specifies the pairing for every element, even though you'll never finish actually performing all the pairings. The rule is what matters. The rule is what proves the bijection exists. And this highlights another aspect of mathematical thinking that the paradox illuminates: the difference between process and structure. Physically carrying out the moves in Hilbert's hotel would be impossible. You can't actually shift infinitely many guests, one by one, because the process would never end. But mathematically, the process doesn't need to be carried out. It only needs to be specified. The rule that says, move from room n to room n plus 1 is sufficient. It tells you what would happen if the process were carried out. It defines the structure of the new arrangement, even though the arrangement itself is never physically realized. This is similar to how we think about infinite sums in mathematics. The sum of 1/2 plus 1/4 plus 1/8 plus 1/16, continuing forever, equals 1. We can prove this without actually adding up infinitely many terms. The proof relies on understanding the pattern, the structure of the sum, not on completing an infinite process. Hilbert's hotel works the same way. We understand the reshuffling through the rules that define it, not by imagining every individual guest moving through every individual doorway. The paradox also invites us to think about potential versus actual infinity, a philosophical distinction that has occupied thinkers for centuries. Potential infinity is the idea that a process can continue without end. You can always add one more, take one more step, count one more number. Actual infinity is the idea that the infinite collection exists as a completed whole, all at once, as a finished totality. Hilbert's hotel treats infinity as actual. The hotel has infinitely many rooms, all existing simultaneously. Every room is already there, already numbered, already part of the structure. The guests move within this completed infinite structure. In some philosophical traditions, actual infinity is considered problematic or even impossible. How can something be both infinite and complete? If it's infinite, doesn't that mean it's unfinished, always growing, never final? But in modern mathematics, actual infinity is a standard concept. Infinite sets are treated as complete objects that can be studied, compared, and manipulated. The natural numbers form an infinite set, a finished, complete collection that contains infinitely many elements. This might seem paradoxical philosophically, but it's coherent mathematically. The set exists as a defined object with specific properties, even though it has no end. Hilbert's hotel embodies this idea of actual infinity. The hotel is complete. It's not under construction, with new rooms being added over time. It already has all its infinitely many rooms, standing there, waiting, available. The paradox operates within this completed infinite space, showing what becomes possible when infinity is treated as an actual existing structure rather than an ongoing, never-finished process. This completeness is what allows the paradox to be so neat, so satisfying in its logic. If the hotel were only potentially infinite, if rooms were added as needed, the reshuffling wouldn't work the same way. The manager would have to build new rooms to accommodate new guests, and the paradox would collapse into something more mundane. But because the infinity is actual, because all the rooms already exist, the manager can perform miracles of reorganization without altering the hotel itself. The paradox also connects to the concept of limits, which is central to calculus and mathematical analysis. A limit describes what happens as a process approaches infinity. For example, as you add more and more terms to the sum 1/2 plus 1/4 plus 1/8 and so on, the total gets closer and closer to 1. The limit of the sum, as the number of terms goes to infinity, is exactly 1. Limits allow us to work with infinite processes in a precise, controlled way. In Hilbert's hotel, the moves can be thought of in terms of limits. When the manager asks everyone to shift one room forward, each individual guest makes a finite move. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3. Each of these is a simple, finite step. But the collection of all these moves, happening simultaneously across infinitely many guests, is an infinite process. The limit of this process, the final configuration, after all moves are complete, is a state where room 1 is empty and every other guest is in the next room up. The limit is well defined and consistent, even though the process involves infinitely many actions. This idea of limits extends throughout mathematics. Integration, the process of calculating areas under curves, involves taking infinitely many, infinitesimally thin slices and summing them up. Derivatives, which describe rates of change, involve looking at infinitely small differences. These concepts work because limits provide a rigorous way to handle infinity, to cross the boundary from the finite to the infinite without losing logical coherence. Hilbert's hotel demonstrates that infinite structures can be manipulated logically, just as limits allow infinite processes to be calculated precisely. The hotel is a discrete, countable infinity, a different kind of mathematical object than the continuous infinity of calculus, but it operates on similar principles. The infinity is structured, governed by rules, and therefore comprehensible. There's also a playful quality to Hilbert's hotel, a sense that mathematics can be creative and imaginative. The paradox is a story, a narrative with characters, the manager, the guests, the buses, even though it's fundamentally about abstract sets and functions. This narrative quality makes the mathematics accessible, giving us a concrete scenario to visualize and follow. The story format doesn't diminish the rigor of the mathematics, it enhances our ability to understand it. This storytelling aspect of mathematics is important. Mathematics is often perceived as dry, formal, disconnected from everyday experience, but thought experiments like Hilbert's hotel show that mathematics can be engaging, surprising, even delightful. The paradox invites you to wonder, to question, to see familiar concepts like fullness and capacity in a completely new light. It turns abstract set theory into something you can almost imagine walking through, room by room, number by number. And yet the paradox never loses its precision. Every claim can be backed up with formal proofs. Every move the manager makes can be described as a function mapping one set to another. The storytelling serves the mathematics, making it clearer and more memorable without sacrificing accuracy or rigor. This balance between accessibility and precision is part of what makes Hilbert's Hotel such an effective teaching tool. The paradox has also inspired variations and extensions. Some versions ask what happens if uncountably many guests arrive. The answer is that the hotel cannot accommodate them, revealing the limits of countable infinity. Some versions explore what happens if guests start leaving, or if the hotel needs to close certain rooms, or if guests want to switch rooms according to various preferences. Each variation probes a different aspect of infinite sets and their properties. These variations show that the paradox is not just a single trick, but a framework for exploration. Once you understand the basic principle that countably infinite sets can be reorganized in surprising ways, you can apply that principle to many different scenarios. You can test the boundaries of what's possible, discover what works and what doesn't, and build a deeper intuition for how infinity behaves. The paradox also highlights the role of structure in mathematics. The hotel works because the rooms are numbered, giving them an order, a sequence. If the rooms were unnumbered, if they existed as an unorganized collection without any indexing system, the reshuffling strategies wouldn't work. You couldn't tell a guest to move to the next room or to double their room number because those instructions rely on the numbering. The structure imposed by the numbering is what makes the infinity manageable. This is a general principle in mathematics. Structure makes infinite objects comprehensible. The natural numbers have structure, the order, the progression, the rules of arithmetic. The real numbers have structure, the continuum, the density, the order. Even though both are infinite, their structure allows us to reason about them, to prove theorems about them, to understand their properties. Structure is what distinguishes different types of infinity, what makes some infinities countable and others uncountable, what determines which operations are possible and which are not. Hilbert's hotel is a structure. It's not a random, formless infinity. It's an organized, numbered, sequential infinity. And because it's structured, it can perform the miracles of reorganization that make the paradox work. The structure is the key to everything. This is the key, reversal, the moment when intuition breaks and something new has to take its place. In finite contexts, if every room is occupied, the capacity is exhausted. Adding one more guest requires adding one more room. But in infinite contexts, being fully occupied and having infinite remaining capacity are not contradictory. The capacity isn't a fixed amount that gets used up. It's a structural property that remains no matter how many times you fill the hotel. You can shift, rearrange, and reorganize without ever running out of space, because there is no edge to run up against. The sequence of rooms never ends, so the moves never have to stop. This doesn't mean that Hilbert's hotel could exist in the physical world. It's a thought experiment, a story told to illustrate a mathematical idea. Real hotels are finite. Real hallways have limits. Real people take up real space, and real buildings have real walls. If you try to build a hotel with infinitely many rooms, you'd run into practical problems long before you reach the infinite part. You'd run out of land, out of materials, out of time to build, out of money to fund the construction. The paradox doesn't claim to describe a possible architecture. It claims to describe a possible logic, a consistent set of rules that applies when you remove the constraint of finiteness. And this is important because mathematics isn't only about describing the world as it is. It's also about exploring the world of ideas, seeing which concepts fit together and which ones produce surprising consequences when pushed to their limits. Infinity is one of those limits. It appears constantly in mathematics, in geometry, where lines extend forever, in calculus, where we study what happens as quantities grow without bound, in number theory, where we prove facts about all the natural numbers, an infinite collection. Understanding how infinity behaves and how it differs from the finite cases we're used to is essential for making sense of large parts of modern mathematics. Hilbert's hotel gives us a gentle way into this understanding. It doesn't require advanced equations or abstract notation. It just requires following a simple story, step by step, and noticing when the outcomes stop matching what we expected. The hotel is full, but it can still fit more guests. The hotel has infinite rooms, but it can reorganize those rooms to create infinite new vacancies. The even numbers are part of the natural numbers, but there are just as many of them. Each of these statements sounds wrong at first, but each one follows logically from the premise of infinite structure. The paradox also highlights the importance of careful reasoning. It's easy to say infinity is weird and leave it at that, treating the whole subject as mysterious or incomprehensible. But the paradox shows that infinity isn't chaos. It's a different kind of order. The moves that the hotel manager makes aren't random or magical. They're systematic, rule-based, and perfectly consistent. Every guest who moves knows exactly where they're going. Every new arrival gets a specific room. There's no ambiguity, no contradiction, no logical breakdown. The rules are just different from the rules we use in everyday life, where finiteness reigns and full means what we think it means. Returning to the practical world, it's worth noting why this paradox doesn't cause problems in real hotels. Real hotels have a specific number of rooms, and once every room is occupied, the hotel is full in the ordinary sense. The manager can't ask guests to shift to higher numbered rooms because there aren't infinitely many higher numbered rooms. The hallway ends, the building has a last room, and so the strategies that work in Hilbert's hotel simply don't apply. The finite world is governed by finite logic, where adding one requires removing one somewhere else, where subsets are always smaller than the sets that contain them, where capacity is a fixed quantity that can be exhausted, but the thought experiment serves a purpose beyond entertainment or puzzlement. It isolates a concept, capacity, occupancy, fullness, and shows how that concept changes when you cross into the infinite. It trains our minds to recognize when our intuition is built on assumptions that don't always hold. In everyday life, we assume things are finite because they always are. We assume full means full because we've never encountered a situation where it didn't. But those assumptions are contingent, not necessary. They apply in the finite realm, and they stop applying when you step outside it. The paradox also reminds us that mathematics is a discipline of definitions and consequences. If you define a hotel as having infinitely many rooms, and if you define each room as being occupied, then certain logical consequences follow. You can derive new truths from those starting points, truths that might feel strange, but are nonetheless valid within the framework you've set up. This is how much of mathematics works. You establish rules, you explore what those rules allow and forbid, and you discover structures and patterns that weren't obvious at the start. Hilbert himself was deeply invested in the foundations of mathematics, in understanding what mathematics is built upon and how we can be certain that our reasoning is sound. The hotel paradox fits into this larger project. It's not just a curiosity or a puzzle. It's a demonstration of how mathematical concepts behave, a test case for our understanding of infinity, a way of making abstract ideas concrete enough to examine closely. In the early 20th century, when Hilbert was working, the foundations of mathematics were being questioned and rebuilt. Paradoxes had emerged in set theory, contradictions that suggested something was wrong with the way mathematicians were reasoning about infinite collections. Hilbert and others worked to create a rigorous foundation that would avoid these paradoxes while preserving the power and utility of infinite sets. The hotel paradox is a benign paradox, one that surprises without contradicting, that challenges intuition without undermining logic. It's an example of how infinity can be strange while remaining perfectly consistent. This distinction between genuine contradiction and mere counterintuitiveness is crucial. A genuine contradiction would be a fatal flaw, a sign that something is deeply wrong with the system. But counterintuitiveness is just unfamiliarity. It's the feeling of encountering something that doesn't match your prior experience, something that requires adjusting your mental models to accommodate. Hilbert's hotel is counterintuitive, not contradictory. It asks you to adjust your understanding of fullness and capacity, to see that those concepts behave differently under infinity but it never asks you to accept a logical impossibility. This capacity for adjustment, for updating our understanding when we encounter new ideas, is part of what makes mathematics a living, evolving discipline. Our intuitions are built from experience, and most of our experience is with finite quantities. But mathematics allows us to go beyond experience, to explore realms that we cannot directly observe or manipulate. Infinity is one such realm. Higher dimensions, complex numbers, abstract algebraic structures, these are others. In each case, we extend our thinking beyond the familiar, guided by logic and structure, rather than direct sensory experience. Hilbert's Hotel is an invitation to make that extension, to step beyond the finite and see what infinity looks like when examined closely. And what it looks like is both strange and orderly, both surprising and consistent, both counterintuitive and perfectly logical. The hotel can be full and still have infinite capacity. This is the central lesson, the core insight that the paradox offers. And once you've understood this, once you've followed the moves and seen how they work, your understanding of infinity has deepened. You've learned something fundamental about how size and structure behave when quantities grow without bound. And perhaps there's something quietly restful in that realization. The paradox doesn't ask you to abandon reason or to accept nonsense. It asks you to follow reason into unfamiliar territory, to see where it leads when the usual constraints are lifted. The infinite is vast, yes, but it's also structured, orderly, knowable in its own way. You can make sense of it if you're patient, if you set aside the expectation that it will behave like the finite quantities you're used to. You can walk through the halls of Hilbert's Hotel, room by room, move by move, and see that even in a place with no end, there's a logic that holds, a coherence that persists, a kind of calm in the endlessness. The story of Hilbert's Hotel is, in the end, a story about letting go of certain expectations and seeing what happens when you do. It's a story about the flexibility of infinite structures, the surprising ways they can be rearranged and reorganized. It's a story about the difference between size as we experience it in daily life, concrete, bounded, exhaustible, and size as it appears in the abstract realm of mathematics, where quantities can grow without limit and sets can contain as many elements as their subsets. It's a story that begins with a simple question: what if a hotel had infinitely many rooms? And unfolds into a series of gentle revelations about what infinity really means. The takeaway isn't that the world is paradoxical in some troubling way, or that logic breaks down when things get too big. The takeaway is that our intuition is calibrated to the finite, and infinity is a different beast entirely. It follows different rules, allows different possibilities, produces different outcomes. But it's not irrational, it's not beyond understanding, it's just beyond the everyday, beyond the realm of things we can touch and count and line up in a row. And by walking through the paradox step by step, by following the moves the hotel manager makes and seeing how they work, we train ourselves to think about the infinite in a clearer, more structured way. Hilbert's Hotel is a place you'll never visit, a building that could never be built, a scenario that will never play out in the physical world. But it's also a place where ideas come into focus, where the abstract becomes almost tangible, where the strange logic of infinity reveals itself through something as ordinary as a guest checking into a room. It's a thought experiment designed to stretch the mind gently, to show that what feels impossible can be perfectly logical once the right framework is in place. And in that sense, it's a kind of gift, a way of seeing beyond the finite limits of everyday life, into a realm where the rules are different but no less real, no less worthy of understanding. As you settle into the quiet of the idea, letting the moves and the numbers and the infinite hallways drift through your thoughts, there's a kind of peace in the consistency of it all. The hotel never runs out of room, the guests never stop moving, the numbers never end. It's a system that sustains itself forever, not through magic, but through structure. Not through chaos, but through order. And perhaps that's the most comforting part of the paradox. Even in the face of infinity, even when things stretch beyond all familiar bounds, there's a logic that holds, a pattern that persists, a sense that the world, whether finite or infinite, can be understood, step by step, room by room, one careful thought at a time. The infinite hallway stretches ahead, doors numbered in perfect sequence, each one leading to another, and another, and another, without end. The guests shift, the numbers double, the buses arrive, and still there's space, always another room, always another move to make. The paradox isn't a problem to be solved, but a perspective to be gained, a way of seeing that what seemed impossible becomes, in the context of infinity, simply the way things are. And in that realization, there's a quiet satisfaction, a gentle acceptance of the strange and beautiful rules that govern the infinite. A sense that even the endless can be known, can be navigated, can be understood with patience and care. So the hotel stands, infinitely tall or infinitely long, its doors numbered forever, its guests endlessly shifting, its capacity never exhausted. And the paradox remains, not as a puzzle that defeats us, but as a lesson that guides us, showing that infinity is not a wall we hit, but a horizon we approach, always revealing more, always offering space, always consistent in its own peculiar logic. The finite world ends, but the infinite world simply continues, room after room, step after step, thought after thought, a calm and endless progression into understanding. The next story is about to begin. Please relax and enjoy. The human mind expects language to behave in certain predictable ways. When we make a statement about the world, we assume it can be measured against reality and assigned a value, true or false. A sentence that says the sky is blue can be checked. A sentence that says water freezes at 0 degrees Celsius can be tested. The system feels stable because there is something outside the sentence, some fact, some condition in the world that determines whether the claim holds up. Truth in this ordinary sense is a relationship between what we say and what is. The sentence points outward, and the world either confirms it or contradicts it. But there exists a sentence that does not point outward. It does not describe the sky or water or any object you could touch or measure. Instead, it turns inward and makes a claim about itself. The sentence is short, almost laughably simple. This statement is false? At first glance, it seems like a minor curiosity, a linguistic trick that might amuse someone for a moment before they move on. But the simplicity is deceptive. This sentence does not behave the way language is supposed to behave. It does not allow you to assign it a truth value and walk away. Instead, it creates a loop, a cycle of reasoning that tightens with every step. And no matter how carefully you approach it, the sentence refuses to settle into either category. It is not a failure of your thinking. It is not a lack of information. It is a structural problem embedded in the sentence itself, and it has troubled philosophers, logicians, and mathematicians for more than 2,000 years. The trouble begins with self-reference. Most sentences point at something else. They describe events, objects, properties, relationships. But this sentence points at itself. The subject of the claim is the claim. The statement is both the thing being evaluated and the tool doing the evaluation. That doubling creates a peculiar tension, because truth is normally a judgment. We apply from the outside. We stand apart from a sentence, compare it to the world, and decide whether it fits. But when a sentence folds back on itself, there is no outside position. You are inside the loop the moment you try to evaluate it. And the loop, as it turns out, has no exit. The paradox is often called the liar paradox, though the name is slightly misleading. There is no liar here, no person making a false claim with intent to deceive. The sentence is not about dishonesty, it is about structure. It is about what happens when language is allowed to reference itself in a particular way, combined with a claim about truth. The ancient Greeks were aware of this problem. Epimenides, a Cretan, is said to have declared that all Cretans are liars, and from that declaration, a version of the paradox emerged. But the clearest, simplest form strips away the cultural context and the human element. It removes the liar and leaves only the loop. This statement is false. 4 words, and the entire edifice of binary truth begins to wobble. Before we trace the reasoning that creates the paradox, it helps to understand what makes this sentence different from the vast majority of statements we encounter. Consider a typical declarative sentence. The cat is on the mat. This sentence has a subject, the cat, and it makes a claim about that subject's location. We can verify the claim by looking at the world. Is there a cat? Is there a mat? Is the cat positioned on the mat? The sentence reaches out into physical space and makes a testable assertion. The truth value depends on correspondence. Does the sentence match the facts? Now consider a sentence like snow is white. This is a general claim about a property of snow. We can test it by examining snow, observing its colour, and comparing that observation to the claim. Again, the sentence points outward. It describes something in the world, and the world either supports the description or contradicts it. The mechanism is straightforward. The sentence is a kind of map, and we check whether the map corresponds to the territory. Even abstract sentences follow this pattern in most cases. 7 plus 5 equals 12 makes a claim about mathematical relationships. We can verify it through calculation, through the axioms of arithmetic, through logical derivation. The sentence points to a mathematical truth, and we can confirm or deny it by examining the mathematical facts. The sentence has content that exists independently of the sentence itself. The number 12 does not depend on anyone saying 7 plus 5 equals 12. The claim is about something external to the claim. But this statement is false does not point outward. It does not describe cats, snow, numbers, or any external facts. It points at itself. The subject of the sentence is the sentence. The claim is about the claim, and that creates a fundamentally different situation. There is no external fact to check. There is no independent reality to consult. The sentence is asking you to evaluate it based on what it says about itself, and what it says about itself is that it is false. The content of the sentence is its own truth value, and that content is self-negating. This self-reference is the key. Without it, there is no paradox. A sentence like "my previous statement was false" can be evaluated if we know what the previous statement was. If the previous statement was "the sky is green," then "my previous statement was false" is true because the sky is not green. The sentence refers to another sentence, and we can break the reference chain by examining the external claim. But this statement is false, has no external reference. The chain loops back immediately. The sentence refers to itself, and only to itself, and that creates a closed circuit. It is worth pausing to appreciate how rare this is. The overwhelming majority of sentences we produce in daily life do not refer to themselves. They refer to objects, events, people, ideas, anything except the sentence itself. Self-reference requires a deliberate act of linguistic construction. You have to design a sentence that points back at itself, and you have to do so explicitly. This statement is false is a deliberately engineered expression. It is not something that arises naturally in conversation. It is a philosophical thought experiment, a test case, a probe designed to reveal something about the structure of truth. And what it reveals, at first contact, is that something is wrong. The sentence feels unstable. It resists evaluation. You can almost feel the logical ground shifting beneath your feet when you try to assign it a truth value. And that feeling is not an illusion. It is a signal that the ordinary rules are not working, that the framework is encountering something it was not designed to handle. Let us try the most natural move first. Suppose the sentence is true. This is the default instinct. Take the sentence at face value. Assume it is telling the truth and see where that leads. If the sentence is true, then what it asserts must be the case. The sentence asserts that it is false. So if we accept that the sentence is true, we are also accepting that the sentence is false. The two conclusions sit side by side, and they are incompatible. A statement cannot be both true and false at the same time, not in the classical framework of logic. The assumption collapses immediately. The moment you grant the sentence the status of truth, it pulls that status away from itself. The mind completes the reasoning, arrives at the conclusion, and then realizes the conclusion contradicts the starting point. It is a kind of logical short circuit, a proof that undoes itself in the act of being proven. There is something almost hypnotic about this step. The reasoning is airtight. Each move follows from the last with perfect clarity. If true, then false. The implication is clean, undeniable, and yet the result is impossible. The feeling is not one of confusion exactly. It is more like watching a mechanism jam. The gears turn smoothly until they lock, and no amount of force will make them continue. You can see the path the logic took. You can follow every link in the chain, and still the chain leads nowhere that makes sense. The sentence seemed to promise a simple evaluation, true or false, but it delivered a contradiction instead. And contradictions, in classical logic, are not allowed. They are the sign that something has gone wrong. But what exactly has gone wrong here? The reasoning is valid. The sentence is grammatically correct. The rules of logic have been followed. And yet the outcome is unacceptable. Let us walk through this step more slowly, because the details matter. We begin with an assumption. The sentence is true. In classical logic, this is a legitimate starting point. We are allowed to assume something provisionally in order to see what follows. This is the basis of proof by contradiction, one of the most powerful tools in logical reasoning. We assume something, derive consequences, and if those consequences lead to a contradiction, we conclude that the assumption must be false. So we assume the sentence, "This statement is false," is true. Now we ask, what does this sentence claim? It claims that this statement is false. The phrase "this statement" refers to the sentence itself. So the sentence is claiming that it itself is false. If the sentence is true, then what it claims must be accurate. And what it claims is that it is false. Therefore, if the sentence is true, it is false. But this is a contradiction. A sentence cannot be both true and false. The law of non-contradiction, one of the foundational principles of classical logic, states that contradictory propositions cannot both be true at the same time. If P is true, then not P is false. If the sentence is true, it cannot also be false. So our assumption has led us to an impossible situation. We have derived a contradiction. In a normal proof by contradiction, this would be the end. We would conclude that our assumption was incorrect. If assuming P leads to a contradiction, then P must be false. So if assuming the sentence is true leads to a contradiction, we should conclude that the sentence is false. And that is exactly what we will try next. But already there is a sense of unease. The contradiction did not arise from some external fact or some additional premise. It arose from the sentence itself, from its own content. The sentence generated its own contradiction, and that is unusual. So we try again. Perhaps the mistake was in assuming the sentence was true. Let us take the opposite path. Suppose the sentence is false. This is the natural counterpoint, the other half of the binary choice. If the sentence is false, then what it claims is not the case. The sentence claims to be false. So if the sentence is false, then the claim, "this statement is false," is incorrect. But if that claim is incorrect, the sentence is not false. It must be true. And if it is true, we are back where we started. The assumption that the sentence is false leads, through the same clean logical steps, to the conclusion that the sentence is true. But we began by supposing it was false. The assumption has generated its own negation. The proof has eaten itself again, but from the opposite direction. Let us trace this path carefully as well. We assume the sentence is false. We ask, what does the sentence claim? It claims to be false. If the sentence is false, then its claim is incorrect. If the claim this statement is false is incorrect, then the statement is not false. If it is not false, and we are working within a binary framework where every statement is either true or false, then it must be true. So if the sentence is false, it is true. Again, a contradiction. We assumed the sentence was false, and we derived the conclusion that it is true. The assumption and the conclusion are incompatible. By the logic of proof by contradiction, we should reject the assumption, but we have now tried both assumptions. We assumed the sentence was true, and that led to a contradiction. We assumed the sentence was false, and that also led to a contradiction. Both paths are blocked. Neither assumption can hold. Now the loop is visible. True implies false. False implies true. The two paths mirror each other, and neither one can hold. Each assumption leads to a conclusion that contradicts the assumption. There is no stable ground. You cannot call the sentence true because calling it true makes it false. You cannot call it false because calling it false makes it true. The sentence oscillates, flipping between the two values without ever settling on one. It is not that we lack the information to decide. It is not that the sentence is vague or ambiguous. The sentence is perfectly clear. The problem is that the clarity produces a contradiction, and the contradiction is baked into the structure of the sentence itself. This oscillation is not a failure of reasoning. The logic is impeccable. Every step is valid. Every inference is justified. The problem is not with the reasoning process. The problem is with the sentence. The sentence has been constructed in such a way that it cannot be consistently evaluated within the classical framework. It is a sentence that the system cannot process without generating contradictions. And that is what makes it a paradox. A paradox, in the strict philosophical sense, is not just a puzzle or a riddle. It is a situation where reasonable assumptions and valid reasoning lead to an impossible conclusion. The assumptions seem innocent, the reasoning seems sound, and yet the result is unacceptable. Something has to give, either the assumptions, or the reasoning, or the framework itself. And in the case of the liar paradox, it is not immediately clear which one should give. The assumptions are minimal. We are simply trying to evaluate a sentence. The reasoning is standard. We are using the basic rules of logic. The framework is classical logic, which has been enormously successful in mathematics, science, and philosophy. And yet this simple sentence breaks it. This is where the paradox earns its power. It is not a trick or a sophistry. It is not a misuse of language or a confusion of terms. It is a genuine problem, a structural flaw that reveals something deep about the relationship between language, truth, and logic. The sentence, "This statement is false," is a kind of limit case, a configuration that the classical framework cannot handle. And the fact that such a configuration can exist, that it can be expressed in ordinary language using ordinary words, is significant. It means that the framework has boundaries. It means that not every sentence can be evaluated as true or false. It means that the concept of truth, which seems so basic and intuitive, is more delicate than it appears. To understand why this is so unsettling, it helps to consider what the classical framework assumes. Classical logic is built on a few foundational principles. One is the law of non-contradiction. No statement can be both true and false at the same time. Another is the law of excluded middle. Every statement is either true or false. There is no third option. These principles seem almost self-evident. They feel like the bedrock of rational thought. And yet the liar paradox appears to violate both of them. If we try to evaluate the sentence, we are forced to say it is both true and false, violating the law of non-contradiction. If we refuse to assign it either value, we violate the law of excluded middle. The The paradox puts us in a position where we cannot uphold both laws simultaneously. This creates a kind of philosophical crisis. If the foundational principles of logic can be challenged by a single sentence, what does that say about logic itself? Is logic a universal framework, applicable to all statements, or does it have limits? Is truth a coherent concept, or does it break down in certain cases? These are not idle questions. They go to the heart of how we understand reasoning, knowledge, and reality. And the liar paradox forces us to confront them. The ancient Greeks were the first to grapple with this problem in a systematic way. The paradox is sometimes attributed to Epimenides of Crete, who supposedly said, "All Cretans are liars." If Epimenides is a Cretan, and all Cretans are liars, then his statement must be a lie. But if his statement is a lie, then not all Cretans are liars, which means his statement could be true. The structure is similar to the liar paradox, though slightly more complex because it involves a quantifier, all Cretans, and a cultural reference. The simpler form, this statement is false, distills the paradox to its essence. The Greek philosopher Eubulides of Miletus, who lived in the 4th century BCE, is often credited with formulating the paradox in its clearest form. Eubulides was a member of the Megarian school, a group of philosophers interested in logic, semantics, and the nature of truth. The Megarians were known for their paradoxes, and Eubulides contributed several, including the Sorite's paradox, the paradox of the heap, and the paradox of the horned man. But the liar paradox is perhaps his most famous legacy. It has survived for more than 2 millennia, and it remains a central problem in philosophy and logic. The Stoics, who came after the Megarians, also wrestled with the paradox. Chrysippus, one of the most important Stoic philosophers, is said to have written extensively on the liar, producing multiple treatises attempting to resolve it. None of these treatises have survived, so we do not know exactly what solutions he proposed. But the fact that he devoted so much attention to the paradox indicates how seriously it was taken. For the Stoics, logic was a crucial part of philosophy, a tool for understanding the world and living a good life. A paradox that threatened the foundations of logic was not a trivial matter. It was a genuine challenge that demanded a response. In the medieval period, the liar paradox was studied intensively by logicians in both the Islamic and Christian traditions. Arabic philosophers like Al-Farabi and Avicenna discussed the paradox and developed sophisticated theories of reference and truth to address it. In the Latin West, medieval logicians devoted enormous energy to what they called insolubles, paradoxes that seemed to resist solution. The liar paradox was the most famous insoluble, and entire treatises were written analysing its structure and proposing ways to resolve it. These medieval logicians developed intricate theories of supposition, which described the different ways terms could refer to things, and they used these theories to try to untangle the self-reference in the liar paradox. One medieval approach was to distinguish between different levels of reference. A term could refer to things in the world, or it could refer to other terms, or it could refer to itself. The liar paradox, according to this analysis, involved a term referring to itself in a problematic way. By carefully tracking the levels of reference and imposing restrictions on self-reference, some logicians hoped to block the paradox. This approach anticipated, in a rough way, the hierarchical solutions that would be developed in the 20th century. But despite centuries of effort, no consensus emerged. The paradox remained unresolved, a persistent thorn in the side of logic and semantics. Different philosophers proposed different solutions, but none was universally accepted. The paradox seemed to resist every attempt to domesticate it. It remained wild, untamed, a reminder that language and logic were more complex and more fragile than they appeared. In the modern period, the paradox took on new urgency because of developments in mathematics and logic. In the late 19th and early 20th centuries, Mathematicians were attempting to place mathematics on a rigorous, logical foundation. The goal was to show that all of mathematics could be derived from a small set of logical axioms, using purely logical rules of inference. This project, known as logicism, promised to eliminate doubt and ambiguity from mathematics. It would show that mathematical truths were logical truths, grounded in the unshakable bedrock of logic itself. But the project ran into problems. One of the most devastating was Russell's paradox, discovered by the British philosopher and mathematician Bertrand Russell in 1901. Russell's paradox is closely related to the liar paradox, though it arises in the context of set theory rather than semantics. The paradox concerns the set of all sets that do not contain themselves. Does this set contain itself? If it does, then it should not, because it is the set of sets that do not contain themselves. If it does not, then it should, because it meets the criterion for membership. The structure is identical to the liar paradox, a self-referential definition that generates a contradiction. Russell's paradox was a crisis for logicism because it showed that naive set theory, the foundation on which mathematics was supposed to rest, was inconsistent. If the foundation was inconsistent, the entire edifice collapsed. Mathematics could not be grounded in logic if logic itself contained contradictions. The paradox forced mathematicians and logicians to rethink their approach. They had to develop more careful, more restrictive systems that avoided the paradoxes. This led to the development of axiomatic set theory, type theory, and other formal frameworks designed to block self-referential contradictions. The most influential response to these paradoxes came from Alfred Tarski, a Polish logician working in the mid-20th century. Tarski's insight was that the liar paradox arises from a confusion of levels. When we talk about the world, we use a language, call it the object language. When we talk about the object language, we use a different language, call it the meta-language. Truth is a predicate that belongs to the meta-language, not the object language. A sentence in the object language cannot make a claim about its own truth, because is true is a meta-language predicate. The liar sentence attempts to collapse this distinction. It tries to use a truth predicate within the object language to make a claim about a sentence in the object language. And that, according to Tarski, is illegitimate. Tarski's solution is to enforce a strict hierarchy of languages. At the bottom is the object language, which talks about the world. Above it is the first meta-language, which talks about the object language and contains the truth predicate for the object language. Above that is a second meta-language, which talks about the first meta-language and contains the truth predicate for the first meta-language, and so on in an infinite hierarchy. At each level, you can talk about the truth of sentences at the level below, but you cannot talk about the truth of sentences at your own level. This blocks the liar paradox, because the sentence, "this statement is false," cannot be formulated. To say, "this statement is false," you would need to use a truth predicate from your own level, but truth predicates only apply to lower levels. Tarski's hierarchy is elegant and powerful. It provides a clear, formal framework for talking about truth without generating paradoxes. And it has been enormously influential in logic and the philosophy of language. But it comes at a cost. The cost is that we lose the ability to talk about truth in a unified way. There is no single truth predicate that applies to all sentences. Instead, there are infinitely many truth predicates, one for each level of the hierarchy, and we cannot step outside the hierarchy to talk about truth in general. We are always at some level, talking about truth at lower levels, but never able to encompass the whole system. This feels unsatisfying to some philosophers. It seems to avoid the paradox rather than resolve it. The liar sentence is ruled out by fiat by a stipulation that sentences cannot refer to their own truth. But why should we accept that stipulation? Natural languages like English do allow sentences to refer to their own truth. We can say this sentence is in English, and there is no paradox. We can say this sentence is true, and while that sentence is odd, it does not generate a contradiction. The problem arises only when we combine self-reference with negation, as in, this sentence is false. So the restriction seems too broad. It rules out more than just the paradoxical cases. Moreover, the hierarchy feels artificial. In ordinary language, we do not carefully track levels and make sure we are using the right truth predicate for each level. We just talk about truth, and most of the time, everything works fine. The hierarchy is a formal device that works well in mathematical logic, but it does not seem to capture the way truth actually functions in natural language. And if the goal is to understand natural language, rather than to construct a formal system, the hierarchy may not be the right tool. Other philosophers have taken a different approach. Instead of ruling out the liar sentence as ill-formed, they accept it as a legitimate sentence, but deny that it must be either true or false. This requires abandoning the principle of bivalence, the principle that every statement is either true or false. If we allow a third option, such as neither true nor false, or indeterminate, or paradoxical, then the liar sentence can be assigned this third value, and the paradox dissolves. This approach is appealing in some ways. It allows us to keep the liar sentence as a meaningful expression while avoiding the contradiction. We do not have to rule it out as nonsense or impose an artificial hierarchy. We simply acknowledge that some sentences do not fit neatly into the true-false dichotomy. They occupy a kind of liminal space, and we need to expand our framework to accommodate them. But this approach also has costs. The principle of bivalence is deeply embedded in classical logic. Many of the rules of inference that we use depend on it. If we abandon bivalence, we have to revise those rules. We have to develop a many-valued logic, a system that can handle 3 or more truth values. And we have to decide how these new truth values interact with the old ones. If a sentence is neither true nor false, what happens when we negate it? What happens when we combine it with other sentences using and or? The answers are not obvious, and different many-valued logics give different answers. Moreover, it is not clear what it means for a sentence to be neither true nor false. In what sense does the liar sentence fail to be true or false? It is not vague, like, John is tall, where the truth value might depend on how we define tall. It is not ambiguous, like, I went to the bank, where the truth value might depend on which meaning of bank we have in mind. The liar sentence is perfectly clear and unambiguous. It is just contradictory. So what does it mean to assign it a third value? Is this a genuine metaphysical category, a real status that some sentences have? Or is it just a formal device, a way of labelling problematic sentences without actually explaining what is going on? These questions do not have easy answers, and that is part of what makes the liar paradox so fascinating and so difficult. It is not a problem that can be solved by a single decisive move. Every solution involves trade-offs. Every approach has strengths and weaknesses. The paradox is a kind of stress test that reveals the limits of our theories. It shows where different theories break down, where they make commitments that might be questioned. Some philosophers have explored an even more radical approach, paraconsistent logic. Paraconsistent logic is a system that allows contradictions without collapsing into triviality. In classical logic, if you accept both a statement and its negation, you can derive any conclusion at all. This is called the principle of explosion. From a contradiction, anything follows. If both P and not P are true, then you can prove Q, where Q is any arbitrary statement. This makes classical logic very intolerant of contradictions. A single contradiction infects the entire system, making it useless. But paraconsistent logic rejects the principle of explosion. It allows you to accept contradictions in a controlled way without everything collapsing. The liar sentence in a paraconsistent framework can be both true and false. The contradiction is real, but it is contained. It does not spread to other parts of the system. You can still reason consistently about most things, even while accepting that some sentences are contradictory. This sounds strange, perhaps even incoherent. How can something be both true and false? Does this not violate the law of non-contradiction, one of the most basic principles of logic? Paraconsistent logicians argue that the law of non-contradiction, like other logical principles, is not absolute. It is a default rule that holds in most cases, but it can be suspended in special cases, like the liar paradox. The contradiction is an exception, a localized anomaly that does not undermine the system as a whole. Paraconsistent logic has found applications in various areas, from computer science to legal reasoning to the philosophy of science. It provides a way to work with inconsistent information without giving up entirely. If you have a database that contains contradictory entries, paraconsistent logic allows you to query the database and get useful results, rather than having the entire system crash. If you have a scientific theory that makes contradictory predictions in certain edge cases, paraconsistent logic allows you to continue using the theory in other contexts while acknowledging the inconsistency. But paraconsistent logic is controversial. Many philosophers and logicians find it deeply counterintuitive. The idea that a statement can be both true and false seems to violate something fundamental about the nature of truth. Truth, they argue, is about correspondence with reality, and reality does not contain contradictions. A cat cannot be both on the mat and not on the mat at the same time, in the same place, in the same respect. So how can a sentence about the cat be both true and false? Defenders of paraconsistent logic respond that the liar paradox is not about cats or mats or any external reality. It is about language, about sentences that refer to themselves. And language, unlike physical reality, can generate contradictions. The contradictions do not reflect inconsistencies in the world. They reflect structural features of language and logic. Paraconsistent logic is a tool for managing those features without pretending they do not exist. Another response to the liar paradox is to deny that it involves a genuine statement at all. According to this view, the sentence, "This statement is false," is not a real proposition. It may look like a statement, it may have the grammatical form of a statement, but it does not succeed in saying anything. It is a kind of pseudo-statement, a linguistic construction that fails to express a complete thought. This is similar to Tarski's approach, but it does not rely on a hierarchy of languages. Instead, it relies on a more general principle. Not every grammatically correct sentence expresses a proposition. Some sentences are defective in a way that prevents them from being evaluated as true or false. This view has some intuitive appeal. When you try to evaluate the liar sentence, there is a sense in which you cannot quite get a grip on it. It slips away. It does not seem to have a stable content. And that might be because it does not have any content. It is a kind of linguistic illusion, a sentence that looks meaningful but is actually empty. The challenge for this view is to explain what makes a sentence meaningful. What is the difference between a genuine statement and a pseudo-statement? The liar sentence uses ordinary words in an ordinary structure. It is not gibberish. It is not a random string of sounds. It seems to mean something. And if it means something, why can it not be evaluated as true or false? The defenders of this view need to provide a principled account of meaningfulness that rules out the liar sentence while preserving other self-referential sentences that are clearly meaningful. Yet another approach is to focus on the pragmatics of language use rather than the semantics of truth. According to this view, the problem with the liar sentence is not that it cannot be assigned a truth value, but that using it involves a kind of pragmatic incoherence. When you assert a sentence, you're implicitly committing to its truth, But if you assert this statement is false, you are committing to the claim that what you are asserting is false. That is a pragmatically incoherent speech act. It is like promising to break your promise or commanding someone not to obey your commands. The sentence might have a meaning, and it might even have a truth value, but the act of asserting it is self-defeating. This pragmatic approach shifts the focus from the sentence itself to the act of using the sentence. It treats the paradox as a problem about what we can coherently do with language, rather than a problem about what sentences can mean or what truth values they can have. And it suggests that the paradox might be resolved, or at least diffused, by paying more attention to the context of use, the intentions of speakers, and the norms of communication. Each of these approaches offers a different perspective on the liar paradox, and each reveals something about the underlying assumptions we make about language, truth, and logic. The paradox is a kind of mirror, reflecting back the structure of our conceptual frameworks. Different frameworks reflect differently, and by examining these reflections, we gain a deeper understanding of what the frameworks are and how they work. One of the remarkable things about the liar paradox is its persistence. Despite more than 2,000 years of analysis, despite the development of sophisticated logical and semantic theories, the paradox remains unresolved in any definitive sense. There is no single solution that all philosophers and logicians accept. Instead, there is a landscape of competing solutions, each with its own strengths and weaknesses, each reflecting different philosophical commitments. The paradox has not been defeated, it has been accommodated in various ways by various systems. But it remains a challenge, a test case, a puzzle that continues to generate new insights. This persistence is not a failure, it is a testament to the depth of the paradox. The liar paradox touches on fundamental issues that do not have simple answers. What is truth? What is meaning? What are the limits of logic? These are not questions that can be settled once and for all. They are questions that each generation of philosophers must grapple with anew, bringing new tools, new perspectives, new ideas. The liar paradox is a constant companion on this journey, a touchstone that helps us measure our progress and test our theories. The paradox also has implications beyond philosophy and logic. It connects to issues in linguistics, computer science, cognitive science, and even physics. In linguistics, the paradox raises questions about the structure of natural language and the limits of semantic theory. Can a theory of meaning handle self-referential sentences? Should it? In computer science, similar paradoxes arise in the context of self-referential programs and recursive definitions. A program that checks whether it will halt faces a paradox, analogous to the liar. In cognitive science, the paradox raises questions about how the mind represents self-referential thoughts. Can we think this thought is false? What happens when we try? In physics, some interpretations of quantum mechanics involve self-referential measurements, where the act of observation affects what is being observed in ways that create loops reminiscent of the liar paradox. These connections suggest that the liar paradox is not an isolated curiosity. It is part of a broader pattern, a family of problems that arise whenever systems fold back on themselves. Self-reference is a powerful and ubiquitous feature of complex systems. It allows systems to represent themselves, to modify themselves, to reason about themselves. But it also creates the potential for paradox, and understanding how to manage that potential is crucial in many domains. In mathematics, self-reference has been both a problem and a tool. Gödel's incompleteness theorems, arguably the most important results in the foundations of mathematics, are based on a kind of self-reference. Gödel constructed a sentence that, in effect, says, "This sentence is not provable in this system." If the sentence is provable, then what it says is false, which means it is not provable, a contradiction. If it is not provable, then what it says is true, which means the system is incomplete. There are true sentences it cannot prove. Gödel used this self-referential construction to show that any consistent formal system powerful enough to express arithmetic is incomplete. There are truths that the system cannot prove. Gödel's proof is a kind of cousin to the liar paradox. It uses self-reference to generate a result that is deeply surprising and profoundly important. But unlike the liar paradox, Gödel's result is not a contradiction. It is a demonstration of a limitation. This sentence is not provable, does not create a paradox because provability and truth are not the same thing. A sentence can be true without being provable. So Gödel's sentence can consistently be true and unprovable. The paradox is avoided, but a remarkable consequence follows. Formal systems have inherent limits. This shows that self-reference, carefully managed, can be a source of insight rather than contradiction. The key is to distinguish between different properties and to avoid collapsing them into each other. Gödel distinguished between truth and provability. Tarski distinguished between different levels of language. These distinctions create space for self-reference to operate without generating paradoxes. But the liar paradox shows what happens when the distinctions are not maintained. When truth folds back on itself without any separation, without any buffer, the result is a loop that cannot be resolved. The paradox also raises questions about the nature of truth itself. What is truth? This is one of the oldest and most central questions in philosophy, and the liar paradox puts pressure on almost every answer that has been proposed. If truth is correspondence with reality, then what reality does the liar sentence correspond to? It does not describe the world, it describes itself. If truth is coherence with other beliefs, then how do we evaluate a sentence that contradicts itself, no matter what we believe about it? If truth is whatever is useful or pragmatically successful, then what use can we make of a paradoxical sentence? The liar paradox does not fit comfortably into any of the standard theories of truth. It is a limit case that exposes the weaknesses of each theory. Some philosophers have concluded that truth is not a single, unified concept. There may be different kinds of truth, or truth may be context-dependent, or truth may be a family of related but distinct notions. The liar paradox, on this view, is a signal that we need a more nuanced, more flexible understanding of truth. We cannot assume that is true always means the same thing, or that it always functions in the same way. Sometimes truth is a matter of correspondence, sometimes coherence, sometimes pragmatic utility, and sometimes, in pathological cases like the liar, truth simply does not apply. This pluralistic approach has its own challenges. If there are multiple kinds of truth, how do they relate to each other? Is there a core concept that unifies them? Or are they fundamentally different? And how do we know which kind of truth is relevant in a given context? Without clear answers to these questions, pluralism can seem more like an evasion than a solution. It avoids the hard work of defining truth by multiplying definitions. Yet there is something appealing about the idea that truth is more complex than it initially appears. Our everyday concept of truth is remarkably robust. We use it constantly in a wide variety of contexts, and it usually works well. But when we push it to its limits, when we test it with carefully constructed cases like the liar paradox, we discover that it has boundaries, that it is not as simple or as universal as we might have thought. And recognizing those boundaries is itself a form of progress. It is a deepening of understanding, a movement from naive confidence to reflective awareness. The liar paradox also invites us to think about the relationship between language and reality. Language is a tool we use to describe reality, to communicate about it, to reason about it. But language is also part of reality. Words are physical sounds, or marks, produced by physical processes in brains and bodies. Sentences are structured sequences of words governed by rules of grammar and semantics. and those rules allow for constructions that do not correspond to anything outside of language. Self-referential sentences are linguistic objects that refer to other linguistic objects, namely themselves. They are not about the world, they are about language, and that creates a kind of autonomy, a space where language operates according to its own rules, independent of external reality. This autonomy is powerful. It allows language to be creative, expressive, flexible. We can use language to talk about imaginary things, to tell stories, to formulate hypotheses, to explore possibilities. We are not limited to describing what is actually the case. We can describe what might be, what could be, what we hope or fear or imagine. Language transcends the immediate, the concrete, the actual. It gives us access to a realm of abstraction and possibility. But this autonomy also creates risks. If language can construct sentences that do not correspond to reality, it can construct sentences that cannot be evaluated by reference to reality. And if we then try to apply concepts like truth, which seem to depend on correspondence with reality, to those sentences, we run into problems. The liar paradox is an example of this risk. It is a sentence that language allows us to form, but that the concept of truth cannot handle. The autonomy of language has generated something that exceeds the capacity of our semantic frameworks. One way to respond to this is to impose limits on language, to restrict what sentences can be formed, to rule out self-referential constructions as illegitimate. This is the approach taken by Tarski's hierarchy and by various formal systems designed to avoid paradoxes. The idea is to bring language back under control, to ensure that every sentence can be evaluated, to prevent the autonomy of language from generating pathological cases. But another way to respond is to accept the autonomy of language and to recognize that not every sentence will fit neatly into our frameworks. Language is richer, more complex, more unpredictable than any formal system we can devise. And that is not a defect, it is a feature. It is part of what makes language such a powerful and versatile tool. The liar paradox, on this view, is not a problem to be solved, but a phenomenon to be understood. It is a reminder that language has its own logic, its own structure, its own possibilities, and those possibilities include configurations that challenge and surprise us. This tension between the desire for control and the recognition of autonomy runs through the entire history of responses to the liar paradox. Formal systems seek control. They want to specify exactly what sentences can be formed, exactly what they mean, exactly what truth values they have. Natural language, by contrast, is wild. It is unpredictable, creative, constantly evolving. It allows speakers to bend rules, to create new expressions, to use language in novel ways. And it allows for sentences like, "This statement is false," which break the neat frameworks we try to impose. Neither approach is clearly right or clearly wrong. Formal systems are essential for certain purposes, especially in mathematics and logic, where precision and consistency are paramount. But natural language is essential for other purposes, especially communication, storytelling, and thought, where flexibility and expressiveness are paramount. The liar paradox sits at the boundary between these two domains. It is a sentence that can be expressed in natural language, but that formal systems struggle to handle. It reveals the gap between the richness of natural language and the precision of formal logic. And it raises the question, should we try to close that gap, or should we accept it as an inevitable feature of the relationship between language and logic? The paradox also has a kind of aesthetic dimension. There is a beauty in its simplicity, an elegance in its structure. 4 words arranged in a particular way create a loop that has fascinated thinkers for millennia. The sentence is clean, minimal, stripped of all unnecessary elements. It is the pure distillation of a logical problem. And that purity gives it a kind of appeal, a charm, that is hard to resist. It is intellectually seductive. It invites you to engage with it, to try to solve it, to see if you can find the key that unlocks the paradox. And even when you discover that there is no simple key, that the paradox resists every attempt at resolution, there is a satisfaction in having grappled with it, in having traced the loops, in having seen the structure clearly. This aesthetic quality is not trivial. It is part of what makes the paradox endure. If it were merely a technical problem, of interest only to specialists, it might have faded into obscurity. But because it's simple and elegant, because it can be appreciated by anyone who understands the concept of truth, it has remained alive, passed down from generation to generation, revisited and re-examined with each new wave of philosophical and logical inquiry. The paradox also serves a pedagogical function. It is an excellent teaching tool, a way to introduce students to the complexities of logic, language, and philosophy. It shows that even simple concepts can hide deep problems. It demonstrates the importance of careful reasoning, of paying attention to structure, of being willing to question assumptions. And it invites students to think for themselves, to engage with a problem that has no authoritative answer, to develop their own views and arguments. In this way, the liar paradox is not just a problem, but an opportunity, a gateway into philosophical thinking. For anyone encountering the paradox for the first time, there is often a moment of disorientation, a sense that something has gone wrong, but it is not clear what. The reasoning seems valid, the sentence seems meaningful, and yet the conclusion is impossible. That disorientation is valuable. It is a sign that the mind is encountering something genuinely new, something that does not fit existing patterns. And it is an invitation to think more deeply, to question assumptions, to explore alternatives. The paradox is a challenge, and challenges are how we learn and grow. There is also a playful quality to the paradox. It has a kind of trickster energy, a mischievousness. It lures you in with its simplicity, makes you think you can solve it easily, and then pulls the rug out from under you. It is frustrating, yes, but the frustration is part of the fun. It is like a magic trick where you know there must be a secret, but you cannot figure out what it is. And even when you learn that the secret is that there is no secret, that the paradox is genuinely paradoxical, there is a kind of delight in the realization. The mind enjoys being surprised, enjoys encountering things that exceed its grasp. This playfulness should not be mistaken for frivolity. The liar paradox is a serious problem with serious implications. But it is also a reminder that intellectual inquiry does not have to be dry or joyless. Thinking can be fun, puzzles can be engaging, and the search for understanding, even when it does not lead to definitive answers, can be deeply satisfying. The paradox also connects to broader cultural and intellectual themes. The idea of self-reference, of something turning back on itself, appears in many contexts beyond logic and language. In art, there are self-portraits, where the artist depicts themselves in the act of painting. In literature, there are stories about storytelling, where the narrative reflects on its own nature. In music, there are compositions that quote themselves, that build structures that fold back on their own beginnings. In film, there are movies that show the making of the movie, that break the fourth wall, that acknowledge their own status as fictions. All of these are forms of self-reference, and they all share something with the liar paradox. They create a loop, a folding back, a structure that points at itself. Self-reference is a way of stepping outside the usual flow, of creating a meta-level, a perspective that looks down on the thing itself. And that perspective can be illuminating, can reveal structures and patterns that are invisible from inside, but it can also be destabilizing, can create ambiguities and paradoxes, can blur the boundaries between levels. The liar paradox is an extreme case where the destabilization is total, where the self-reference generates a contradiction that cannot be resolved. But it is part of a larger pattern, a broader fascination with loops and recursion and self-reflection. In mathematics, recursion is a fundamental concept. A recursive definition defines something in terms of itself. The factorial function, for instance, is defined recursively. The factorial of n is n times the factorial of n minus 1. This looks like a circular definition, but it works because there is a base case, the factorial of 0 is 1, that stops the recursion. Without the base case, the definition would loop forever, never reaching a definite value. The liar paradox is like a recursive definition without a base case. It refers to itself, but there is nothing to stop the loop, nothing to ground the reference. The recursion spirals endlessly, never settling. In computer science, recursion is a powerful programming technique, but it can also create problems. A recursive function that calls itself without a proper stopping condition will run forever, consuming resources until the system crashes. This is called infinite recursion, and it is a bug. Programmers have to be careful to ensure that recursive functions have base cases that the recursion eventually terminates. The liar paradox is like a program with infinite recursion. It loops endlessly, never reaching a stable state, never producing a usable output. These connections suggest that the liar paradox is not an isolated anomaly. It is an instance of a broader class of problems that arise whenever systems involve self-reference or recursion. Understanding the paradox can help us understand these other problems, and vice versa. The tools and techniques developed to handle the liar paradox, hierarchies, restrictions on self-reference, many-valued logics, para-consistent systems, can be adapted and applied in other domains. And insights from those other domains can be brought back to shed new light on the paradox. For instance, the concept of a strange loop, introduced by the cognitive scientist Douglas Hofstadter, is closely related to the liar paradox. A strange loop is a hierarchical system where by moving up or down through the levels, you eventually arrive back where you started. The Escher staircase that goes up and up but returns to its starting point is a strange loop. The video camera pointed at its own screen, creating an infinite regress of images, is a strange loop, and the liar sentence, which refers to itself in a way that creates an unresolvable oscillation, is a strange loop. Hofstadter argued that strange loops are central to consciousness, that the self is a strange loop, a system that represents and reflects on itself in a way that creates a kind of circularity. Whether or not that is correct, the concept highlights the importance of self-reference and the problems it can create. The liar paradox also appears in discussions of truth in religious and mystical contexts. Some traditions emphasize the limits of language, the idea that ultimate truths cannot be captured in words. The liar paradox can be seen as an illustration of this principle. It shows that language, when pushed to its limits, breaks down. It cannot capture every truth, cannot handle every configuration. There are things that slip through the net, that escape linguistic expression. This is not a defect of language, but a reflection of its nature. Language is a finite tool, and it cannot encompass the infinite. The liar paradox is a reminder of that finitude, a sign that points beyond language to something language cannot grasp. This perspective is different from the logical and philosophical approaches, but it is not entirely disconnected. It shares the recognition that the liar paradox reveals limits, boundaries, edges. Whether those edges are logical, linguistic, or metaphysical is a matter of interpretation. But the phenomenon is the same, a sentence that resists the frameworks we use to understand it, that points to something beyond those frameworks. In the quiet of contemplation, the liar paradox can be a kind of meditation object. Like a koan in Zen Buddhism, It is a puzzle that cannot be solved by ordinary reasoning. The more you think about it, the more it slips away. And that slipping away can be instructive. It can teach you about the limits of thought, about the places where logic ends and something else begins. It can cultivate a kind of intellectual humility, a recognition that not everything can be understood, that some mysteries remain. This meditative quality is part of what makes the liar paradox suitable for a sleep-friendly narration. It is a problem that does not demand urgency. There is no need to solve it tonight or ever. You can turn it over in your mind, trace the loops, appreciate the structure, and let it be. There is a calmness in that acceptance, a peace in recognizing that the paradox is what it is, that it will not change, that it does not need to be fixed. The loop continues, the oscillation persists, and that is fine. It is part of the landscape of thought, a feature of the terrain, something to be acknowledged and appreciated rather than eliminated. The paradox also invites us to think about the nature of problems themselves. What makes something a problem? Usually, we think of problems as obstacles to be overcome, challenges to be met, difficulties to be resolved. But the liar paradox is a different kind of problem. It is not a barrier to progress. It does not prevent us from doing anything important. It is more like a marker, a signpost that says, here is an edge, a boundary, a place where the usual rules do not apply, and recognizing that boundary is itself valuable. It tells us something about the territory, about the structure of the conceptual landscape. It maps the limits of our frameworks. In this sense, the liar paradox is not a problem to be solved, but a feature to be understood. It is a permanent part of the logical landscape, a fixture that will always be there, no matter how much we refine our theories. And that permanence is not a failure. It is a success of a different kind. It is the success of having identified something real, something stable, something that persists across different frameworks and different approaches. The paradox is a touchstone, a reference point, a constant against which we can measure our theories. The history of philosophy is full of problems like this, problems that do not admit of definitive solutions, but that continue to generate insight and understanding. The problem of free will, the mind-body problem, the problem of induction, these are all questions that have been debated for centuries without resolution. And yet the debates have been enormously productive. They have led to new concepts, new arguments, new ways of thinking. The liar paradox is in this tradition. It is a problem that does not go away, but that continues to teach us, to challenge us, to deepen our understanding. There is also a kind of comfort in the fact that some problems are permanent. It means that there is always more to think about, always more to explore. The intellectual landscape is not a finite territory that can be fully mapped and exhausted. There are always edges, always frontiers, always mysteries. And the liar paradox is one of those mysteries. It is a reminder that thinking is an ongoing process, not a destination. There is no final theory, no ultimate framework, no end to inquiry. There is only the journey, the exploration, the perpetual engagement with questions that matter. This perpetual quality is soothing in a way. It takes the pressure off. You do not have to solve the liar paradox. You do not have to arrive at the correct answer. You can simply appreciate it, engage with it, learn from it. The paradox is not a test you have to pass. It is an invitation to think, to wonder, to explore. And that invitation is always open. The paradox will still be there tomorrow, and the day after, and 100 years from now. It is patient. It does not hurry. It simply waits, ready to engage with anyone who approaches it with curiosity and care. In the context of sleep, this patience is especially valuable. The mind preparing for rest does not need urgent problems or pressing demands. It needs gentle engagement, calm reflection, a soothing rhythm. The liar paradox, with its quiet loop and its endless oscillation, provides that. It is a thought that can be held lightly, turned over slowly, set down, and picked up again. There is no rush, there is no deadline. There is only the gentle movement of thought, tracing the same path over and over, finding a kind of peace in the repetition. The paradox also connects to the experience of falling asleep itself. Sleep is a kind of loop, a daily cycle of waking and sleeping, consciousness and unconsciousness. The mind winds down, thoughts slow, awareness fades, and then, after a period of rest, the mind winds back up. Thoughts resume, awareness returns. The cycle repeats, day after day, throughout a lifetime. It is a loop without a clear beginning or end, a pattern that continues as long as life continues. And within sleep, there are deeper loops. The stages of sleep cycle through the night, from light sleep to deep sleep to REM sleep and back again. Dreams arise, vivid and strange, and then fade as the sleeper shifts to a different stage. The mind in sleep is not shut off, but actively cycling through different states, different modes of being, and those cycles, like the logical loop of the liar paradox, do not have a simple resolution. They simply continue, unfolding according to their own rhythms. There is something fitting about contemplating the liar paradox as you drift towards sleep. Both involve loops, cycles, patterns that repeat. Both involve a kind of letting go, a release of the need for resolution. In sleep, you do not try to control your thoughts. You let them wander, let them fade, let them dissolve into the formless void of unconsciousness. And in contemplating the paradox, you let go of the need to solve it, to pin it down, to force it into a category. You simply let it be what it is, a loop, a cycle, a pattern that continues. The liar paradox, in the end, is a teacher. It teaches about language, about logic, about truth. It teaches about limits, about boundaries, about the edges of our conceptual frameworks. It teaches about self-reference, about recursion, about the strange loops that arise when systems fold back on themselves. And it teaches about acceptance, about humility, about the recognition that not everything can be controlled or resolved. These are valuable lessons, and they are lessons that do not need to be learned all at once. They can be absorbed slowly, over time, through repeated engagement with the paradox. Each encounter with the paradox reveals something new, or reinforces something already learned. The first time you meet it, you might be puzzled, disoriented, unsure what to make of it. The second time, you understand the structure better, see the loop more clearly. The third time, you appreciate the elegance, the simplicity, the power. With each return, the paradox becomes more familiar, more comfortable, more like an old friend. And that familiarity does not diminish its value. It deepens it. The paradox is not a one-time revelation. It is a companion for the journey, a presence that accompanies you through the landscape of thought. In the stillness of night, with the world quiet and the mind calm, the liar paradox offers a kind of gentle companionship. It does not demand anything. It does not insist on resolution. It simply presents itself over and over in its perfect paradoxical form. This statement is false. True implies false. False implies true. The loop continues, the oscillation persists, and there is a kind of peace in that persistence. It is a reminder that some things do not change, that some patterns endure, that some mysteries remain. And as the mind traces that loop, following the path from true to false and back again, thought slows, awareness softens, and the boundaries between waking and sleeping begin to blur. The paradox becomes a rhythm, a gentle pulse, a cycle that carries the mind toward rest. The loop does not end, but it does not need to end. It simply continues, as it always has, as it always will, a quiet presence in the landscape of thought, a companion on the journey toward sleep.